Level 1. Why we sleep. Over the next couple hours, you'll discover 100 mysteries that keep the world's smartest people awake at night. Not ghost stories or conspiracy theories. These are verified phenomena that defy our best scientific models, constants that shouldn't exist, and questions so fundamental that answering them would rewrite textbooks. Starting with something you'll do tonight. You spend roughly 1/3 of your life unconscious, lying motionless while your brain produces vivid hallucinations. Your muscles become paralyzed, and your core body temperature drops. An extraordinarily vulnerable state that evolution somehow decided was worth the risk. Scientists have been studying sleep for over a century, mapping brain waves, tracking REM cycles, documenting what happens when you're deprived of it. Yet, despite thousands of research papers and countless theories, there is no scientific consensus on why we actually need to sleep. We know what happens during sleep: memory consolidation, cellular repair, waste clearance from the brain. But these are descriptions of the process, not explanations for why consciousness must shut down entirely for 8 hours. No other biological imperative is this poorly understood, and the fact that you can't survive more than a few weeks without it makes the mystery even more unsettling. Level 2. Why we yawn. You've yawned thousands of times in your life, probably yawned while reading that sentence, yet neuroscience cannot definitively explain why your jaw involuntarily stretches open, your eyes squeeze shut, and your lungs pull in a deep breath for no apparent respiratory reason. The leading theories, cooling the brain, increasing oxygen, stretching facial muscles, all sound plausible until you examine the data and realize none of them fully account for the phenomenon. Brain cooling theory predicts yawning should increase in hot environments, but it doesn't. Oxygen theory predicts exercise should trigger yawning, but it rarely does. What makes it stranger is the contagion effect. Seeing someone yawn, hearing someone yawn, even reading about yawning activates mirror neurons in your brain that make you yawn in response. A social synchronization behavior that crosses species boundaries. Dogs yawn when their owners yawn, suggesting some deep evolutionary function that we've completely failed to identify. The mechanism is well mapped, the triggers documented, but the fundamental question of why this reflex exists remains unresolved, hiding in plain sight. Level 3. The placebo effect. When you give someone a sugar pill and tell them it's a painkiller, roughly 30% of people will experience measurable pain reduction. Not imagined relief, but actual changes in brain chemistry, neurotransmitter release, and inflammatory markers that show up on medical scans. This should not be possible under our current understanding of pharmacology. Yet the placebo effect is so reliable that every drug trial must account for it, and in some conditions like depression and chronic pain, placebos perform nearly as well as FDA-approved medications. The effect strengthens with ritual. Bigger pills work better than small pills. Injections work better than pills. Surgery works better than injections, even when all of them are fake. Color matters. Blue pills are better sedatives. Red pills are better stimulants. Price matters. Expensive placebos outperform cheap ones. Doctor demeanor matters. Warm, confident physicians generate stronger placebo responses than cold, uncertain ones. What we're seeing is the brain's expectation system directly altering physiology in ways that shouldn't be medically possible. A self-fulfilling biochemical prophecy that suggests consciousness has far more control over the body than materialist models allow for. Level 4. Why anesthesia works. Every year, millions of people undergo surgery while under general anesthesia, a drug-induced state where you lose consciousness, feel no pain, form no memories, and wake up hours later with no subjective experience of time passing, as if you blinked and suddenly it's over. Anesthesiologists have refined the dosing to a science, can predict almost exactly how much propofol or sevoflurane you'll need based on your weight and metabolism, can keep you hovering at the edge of consciousness for hours without ever waking up or going too deep. What they cannot tell you is how any of it actually works. We know which receptors the drugs bind to, know which neural pathways they disrupt, can describe the cascade of inhibitory signals that spread through the cortex and thalamus, but we have no unifying theory that explains how these molecular interactions translate into the complete dissolution of subjective awareness. Some anesthetics suppress thalamic activity, others enhance inhibitory neurotransmitters, others disrupt neural oscillations. Completely different mechanisms producing the same endpoint, which suggests we're suppressing a symptom of consciousness rather than targeting its source. Operating a machine we don't fully understand. Level 5. Why we dream. Every night, your brain generates elaborate narratives populated by people you know, places you've never been, and events that follow their own bizarre internal logic. Deceased relatives appear alive, you fly without question, time collapses and expands. Impossible physics govern reality, and none of it strikes you as strange until you wake up and the dream evaporates like smoke, leaving only fragments behind. Despite decades of sleep research, no scientific consensus exists on why this happens. Freud thought dreams were unconscious wishes. Neuroscientists thought they were random neural firing. Modern researchers think they consolidate memories, process emotions, simulate threats, rehearse social scenarios. Every theory explains some dreams but not others, and none of them account for the vivid, emotionally charged, narratively structured experience that feels undeniably meaningful even when it makes no logical sense. The brain expends enormous energy creating these nightly hallucinations, suggesting they serve some critical function. Yet you can suppress REM sleep for weeks and suffer surprisingly few cognitive consequences, which implies either dreams are evolutionary byproducts or their function is so subtle we haven't identified the right metrics to measure. Level 6. Left-handedness. Roughly 10% of the human population prefers using their left hand for writing, throwing, and fine motor tasks, a ratio that's remained stable across cultures, centuries, and continents, suggesting some genetic or developmental mechanism that consistently produces this minority. What evolutionary biology cannot explain is why this trait persists at all. In a right-handed world, left-handed people face disadvantages, higher accident rates using tools designed for righties, historical stigmatization, even slightly reduced lifespan in some studies. Natural selection should have eliminated this trait millennia ago, yet it endures at a stable frequency that implies some balancing advantage. Theories abound. Left-handedness might correlate with enhanced creativity, faster reaction times in combat sports, advantages in cooperative tool use where handedness diversity benefits the group. But none of them hold up under rigorous testing. Genetic studies identify contributing factors but no single handedness gene, and identical twins sometimes differ despite sharing DNA, pointing toward developmental randomness rather than pure inheritance. A biological quirk with no clear purpose that evolution has decided to keep around anyway. Level 7. The origin of life. At some point, roughly 3.8 billion years ago, on a planet covered in lifeless oceans, chemistry became biology. Non-living molecules arranged themselves into the first self-replicating system, crossed a threshold that had never been crossed before, and initiated a process that eventually led to every living thing, including you. Scientists have recreated pieces of this transition in laboratories. RNA molecules that can catalyze their own replication. Lipid membranes that spontaneously form enclosed compartments. Amino acids that assemble under simulated early Earth conditions. What nobody has done is put all the pieces together into a plausible pathway from chemistry to life. The problem is not lack of possible explanations, but an overwhelming abundance of them. Metabolism, first theories, RNA world theories, clay template theories, deep sea vent theories, panspermia theories, each explaining part of the puzzle while creating new problems elsewhere. To get a self-replicating system, you need information storage, catalytic activity, compartmentalization, and energy flow, all working simultaneously. Yet each component depends on the others existing first, creating a chicken and egg problem that 70 years of research hasn't resolved. Life happened once, and we still don't know how. Level 8. Déjà Vu. You walk into a room, and suddenly the present moment feels like a memory. The conversation you are having, the position of objects, the angle of light all trigger an overwhelming sense that you've experienced this exact scenario before, even though you rationally know you haven't, creating a disorienting temporal glitch that lasts a few seconds before dissolving completely. Roughly 2/3 of people report experiencing this at least once, making it common enough to warrant scientific explanation. Yet neurology has no definitive model for what's happening. The most popular theory suggests a mismatch in neural timing. Information reaches your memory storage circuits milliseconds before reaching conscious awareness, creating a false sense of recognition. Your brain mistaking the present for the past because of a processing delay too brief to consciously detect. But this doesn't explain why déjà vu correlates with temporal lobe activity, increases under stress and fatigue, or sometimes comes with an eerie sense of knowing what happens next. Some neurologists think it's a glitch in pattern-matching systems. Others think it's cross-activation between recognition and familiarity circuits, and none of them can explain why it happens in this specific, consistent, universally recognizable way. Level 9. Why ice is slippery. You've walked on ice, slipped on ice, probably fell on ice at some point in your life, experiencing firsthand the nearly frictionless surface that makes frozen water uniquely difficult to navigate. Yet the scientific explanation for this everyday phenomenon has been debated for over 150 years. The traditional story taught in schools, that pressure from your foot melts a thin layer of ice, creating liquid water you slide on, turns out to be mostly wrong. The pressure melting effect only works at temperatures close to freezing and requires far more pressure than your body weight provides. Modern theories focus on a pre-existing liquid-like layer that exists on ice surfaces, even at temperatures well below freezing. A quasi-liquid film, only nanometers thick, where water molecules aren't quite solid and aren't quite liquid, vibrating in a disordered state that acts as a lubricant. But why ice develops this surface layer and most other frozen materials don't remains an open question in materials science, connected to deeper mysteries about how water behaves at interfaces, how crystalline structures interact with atmosphere, and why H2O, the most studied molecule on Earth, still produces surprises. Level 10. Ball lightning. For centuries, people have reported seeing glowing spheres of light, basketball-sized, orange or blue-white, silent or hissing, appear during thunderstorms, float through the air in defiance of wind currents, pass through windows and walls without breaking them, persist for several seconds before vanishing or exploding, leaving behind a smell of ozone and sulfur. Thousands of eyewitness accounts describe the phenomenon with remarkable consistency across cultures and time periods. Yet scientists have never successfully captured ball lightning on controlled instruments or reproduced it reliably in laboratory conditions. Proposed explanations range from vaporized silicon in soil creating luminous plasma, to quantum effects in atmospheric electricity, to microwave radiation trapped in plasma shells, to hallucinations caused by magnetic field exposure, each theory accounting for some observations while failing to explain others. The evidence strongly suggests ball lightning is real, not mass hallucination or misidentified conventional lightning. Yet it remains one of those phenomena that exists in the frustrating gap between documented observation and scientific explanation. A natural event that happens frequently enough to be cataloged, but rarely enough to evade systematic study. Level 11. Animal migration. Navigation. Monarch butterflies born in Canada fly 3,000 miles to a specific grove of trees in Mexico they've never seen, using navigation systems encoded in bodies that weigh half a gram and live for only a few weeks. Sea turtles hatch on a beach, swim into the open ocean for decades, then return to that exact beach, sometimes the exact same stretch of sand, to lay their own eggs, crossing thousands of miles of featureless water with pinpoint accuracy. Salmon swim upstream to spawn in the precise creek where they were born, distinguishing it from thousands of identical streams by mechanisms we still don't fully understand. Scientists have documented these migrations for over a century, tracked animals with GPS, measured their responses to magnetic fields, identified magnetoreceptor proteins in their cells. Yet the complete navigation system remains mysterious. Some species use the sun's position, others use star patterns, others use Earth's magnetic field, others use smell, and many use all of these simultaneously in ways that create redundancy we can't fully map. The navigational precision exceeds anything human technology achieved until GPS satellites, accomplished by creatures with brains smaller than a peppercorn. Level 12. The Tunguska Event. On June 30th, 1908, something exploded over Siberia with the force of 15 megatons, roughly 1,000 times more powerful than the Hiroshima bomb, flattening 80 million trees across 830 square miles in a radial pattern, producing seismic waves detected across Europe and Asia, generating atmospheric pressure changes recorded in Britain, creating glowing night skies visible from London to Moscow for 3 days afterward. No crater was ever found. The first scientific expedition didn't reach the site until 1927, 19 years after the event, by which time the forest had begun regrowing and physical evidence had degraded. But the fallen trees still pointed away from the explosion center like compass needles marking ground zero. The leading theory, an asteroid or comet airburst, exploding several miles above the surface, explains most of the evidence, but not all of it. No definitive meteorite fragments have been recovered despite extensive searches. The explosion occurred at exactly the altitude and trajectory that would minimize ground impact if something were trying to avoid detection. And eyewitness accounts describe the object changing direction before detonation. Details that don't fit the simple asteroid explanation and keep alternative theories circulating. Level 13. Why we itch. That crawling sensation on your skin, the overwhelming urge to scratch, the relief when you finally do. Itching is one of the most basic sensory experiences. Yet neuroscience cannot fully explain why it exists as a distinct sensation separate from pain, touch, or temperature. Itch has dedicated neural pathways, specific receptors, unique neurotransmitters, suggesting it evolved for some critical protective function, but that function remains unclear. The obvious answer, itching, alerts you to parasites, irritants, or skin damage, doesn't explain why scratching relieves it, why some itches have no physical cause, or why seeing someone else scratch makes you itch through pure observation. Chronic itch patients sometimes scratch through skin layers down to muscle, suggesting the itch signal can override pain and self-preservation in ways that make no evolutionary sense. Phantom limb patients report itching in amputated arms they can't scratch, creating an impossible sensation with no clear origin. Brain scans show itch activates different regions than pain, despite traveling some of the same pathways, pointing toward a dedicated itch processing system whose purpose we've only begun to map. Level 14. The Bloop. In 1997, underwater microphones throughout the Pacific, part of a military submarine tracking array, detected an ultra-low-frequency sound that rose rapidly in frequency over 1 minute before fading to silence. The sound was powerful enough to register on sensors over 3,000 miles apart, triangulating to a remote point west of Chile, at a volume that dwarfed anything previously recorded in the ocean. Marine biologists recognized the audio signature as biological. It matched the pattern of marine mammal vocalization, rising and falling the way whale songs do. But no known animal could produce a sound this loud. The blue whale generates calls that travel hundreds of miles, but the bloop exceeded blue whale capacity by an order of magnitude, implying a source animal several times larger than anything known to exist. Follow-up investigations suggested ice quakes, glacial ice fracturing underwater, producing acoustic signatures that mimic biological sounds, as the likely explanation. But the source point sits in deep ocean far from major ice formations, and the frequency pattern remains eerily similar to living vocalizations. Level 15. Coral synchronous spawning. Once a year, usually in November, on the night following a full moon, reefs across vast stretches of ocean release eggs and sperm simultaneously. Corals, separated by hundreds of miles, coordinate their reproduction to within the same hour, turning the water milky white with gametes, creating underwater blizzards of genetic material that combine and form the next generation. This synchronized spawning happens across entire species ranges, even among coral colonies that have no chemical or physical contact with each other, suggesting some external timing mechanism that all corals can detect. Moon phase clearly plays a role. Spawning always occurs a few nights after the full moon, but corals lack eyes, lack central nervous systems, lack any obvious way to measure lunar cycles beyond detecting slight variations in nighttime light levels filtering through seawater. Temperature matters, seasonal cues matter, day length matters. Yet none of these factors fully explain the precision. Corals raised in laboratory conditions with controlled light cycles still spawn on schedule, implying an internal biological clock that counts days, tracks moon phases, and triggers reproduction based on astronomical cues that the coral organism itself cannot perceive in any conventional sense. Level 16. Why knuckles crack. When you pull your finger joint apart, you hear a sharp popping sound, feel a satisfying release of pressure, and temporarily cannot crack that same knuckle again for 15 to 20 minutes, while something resets inside the joint capsule. This universal experience remained scientifically unexplained until 2015, when MRY scans captured the exact moment of cracking and revealed gas bubbles rapidly forming in the synovial fluid, a process called cavitation, where negative pressure inside the joint creates a void that collapses with an audible pop. Problem solved, except not entirely. The bubble formation theory explains the sound, but doesn't explain why some people can crack their knuckles dozens of times a day, while others cannot. Why the ability correlates weakly with joint flexibility. Why the temporary refractory period exists, or whether the practice causes long-term joint damage. A question asked by generations of parents and answered with contradictory research. Some studies show no correlation between knuckle cracking and arthritis. Others suggest possible ligament loosening over decades, and none of them explain the underlying question. Why did evolution create joints that produce this satisfying pop in the first place, if it serves no biomechanical function? Level 17. The Taos Hum. In the early 1990s, residents of Taos, New Mexico began reporting a persistent low-frequency humming sound, described as similar to a distant diesel engine, audible indoors but not outdoors, louder at night, strong enough to disrupt sleep and cause health problems. Only about 2% of the population could hear it, but those who could described it with remarkable consistency. Roughly 50 to 80 hertz, continuous, seemingly sourceless, impossible to escape. Investigators ruled out industrial equipment, power lines, and military installations, finding no external sound source that matched the frequency or distribution. Acoustic measurements detected no unusual ambient noise. The hum was real to those who heard it, but invisible to instruments, suggesting either an internal auditory phenomenon, tinnitus, tensor tympani spasms, spontaneous otoacoustic emissions, or an environmental factor affecting only people with specific sensitivities. Similar hums have been reported in Bristol, Windsor, and Bondi, with the same pattern. A small percentage of residents driven to distraction by a sound most people cannot detect. Investigations that find nothing, and no definitive explanation. Level 18. Why zebras have stripes. For over 150 years, naturalists have debated why zebras evolved stark black and white striping, while other African ungulates developed solid coats, a pattern so distinctive it defines the species, so metabolically expensive to produce that it must serve some survival advantage. Yet every proposed explanation has significant holes. Camouflage seems obvious until you realize zebras live on open savanna, where stripes make them more visible. Predator confusion theory suggests the stripes create optical illusions when the herd runs, making it harder for lions to target individuals. But this doesn't explain why stripes evolved when solid coloring would provide better static camouflage. Temperature regulation theory proposes that black and white stripes create convection currents that cool the zebra, except measurements show negligible temperature differences. The most recent research points toward biting fly deterrents. Tsetse flies and horseflies avoid landing on striped surfaces in controlled experiments, possibly because the pattern disrupts their motion detection. But this raises new questions. Why would stripe evolution be driven by insects rather than large predators? And why don't other prey species with similar parasite problems show the same adaptation? Level 19. The Mpemba effect. Under certain conditions, hot water freezes faster than cold water. A statement that sounds wrong, violates basic thermodynamics, seems like the kind of claim that should be immediately disprovable. Yet it's documented, reproducible, and named after a Tanzanian student who observed it in 1963 while making ice cream. Erasto Mpemba noticed that hot ice cream mix froze faster than cold mix, mentioned it to a visiting physicist, and sparked decades of research into a phenomenon that shouldn't happen, but sometimes does. The effect is maddeningly inconsistent. It works with some water samples, but not others. Appears under certain container shapes and cooling conditions, but not universally, and has been explained by evaporation, convection currents, dissolved gases, supercooling, hydrogen bonding, and none of these explanations fully account for when it happens and when it doesn't. A 2016 study offered a molecular explanation involving hydrogen bond strength and energy distribution, but other researchers couldn't replicate the results. The frustrating truth is that hot water freezes faster than cold water is sometimes true and sometimes false, depending on variables we still haven't identified, making it a phenomenon that exists at the intersection of physics and chaos theory. Level 20. Why cats? Purr. That low rhythmic vibration your cat produces when content, a sound generated at 25 to 50 hertz, continuous for minutes or hours, audible from across the room, operates through a mechanism that took until the 21st century to fully understand. Cats don't have a dedicated purring organ. Instead, they vibrate their laryngeal muscles at precise frequencies, creating turbulent airflow through the glottis on both inhale and exhale, producing a sound that originates deep in the throat and resonates through the entire body. We know how it works mechanically, but we still don't know why cats evolved this specific vocalization or what function it serves beyond communication. Purring happens when cats are content, but also when they're stressed, injured, giving birth, or dying. Contexts so varied that contentment signal doesn't capture the full picture. Recent research suggests purring might promote bone density and tissue repair through low-frequency vibration, essentially a self-healing mechanism that happens to double as social signaling. But this theory doesn't explain why no other mammal evolved the same adaptation, or why the frequency range sits precisely in the range known to accelerate healing in human bone fractures. A coincidence that seems almost too convenient. Level 21. Earthquake lights. Minutes before major earthquakes, witnesses sometimes report seeing luminous phenomena in the sky. Glowing spheres, sheet lightning without clouds, flickering columns of light rising from the ground. Visual displays that have been documented for centuries but remained scientifically unexplained until recently. Video footage from the 2007 Peru earthquake, the 2008 Sichuan quake, and the 2011 Japan earthquake captured these lights on camera, confirming they're real physical events rather than optical illusions or mass hysteria. The current theory involves piezoelectric effects. When tectonic stress compresses certain rock types, particularly basalt and gabbro, the intense pressure generates electrical charges that propagate to the surface faster than seismic waves, ionizing air molecules and creating visible light. This explains the timing. Lights appear before the shaking starts, and the geographic distribution. Lights cluster near fault lines with specific rock compositions. What it doesn't fully explain is the variety of forms these lights take, why they appear before some earthquakes but not others of similar magnitude, or how electrical charges several kilometers underground create atmospheric phenomena visible from miles away, suggesting our model captures a part of the mechanism while missing crucial details. Level 22. Why humans are bipedal. Walking upright on two legs is metabolically inefficient compared to quadrupedal locomotion, exposes vital organs, creates back problems, complicates childbirth, and makes us slower than virtually every predator and prey species we encounter, yet somewhere around 6 million years ago, our ancestors committed to this biomechanical disadvantage and never looked back. The traditional explanation, bipedalism freed our hands for tool use, gets the timeline wrong, because stone tools appear 2.5 million years after bipedalism evolved, meaning our ancestors walked upright for millions of years before developing the technology that supposedly justified the adaptation. Alternative theories propose thermoregulation. Standing upright reduces sun exposure on the savanna, but this doesn't explain why other savanna mammals didn't evolve the same solution. Some researchers point to wading and swimming in shallow water as the original selective pressure. Others suggest social display and height advantages in tall grass. Others emphasize energy efficiency over long distances despite higher energy cost per stride. The frustrating reality is that bipedalism created the conditions for everything that makes us human. Large brains, complex tool use, language. But we still don't know what initial advantage drove the first ape to stand up. Level 23. The Hessdalen Lights. In a remote Norwegian valley, unexplained lights have appeared regularly since at least the 1930s. Floating orbs that hover, dart, split apart, merge together, and vanish, sometimes lasting seconds, sometimes persisting for over an hour, visible to the naked eye and documented by automated monitoring stations that have operated continuously since the 1980s. The Hessdalen phenomenon is unique among unexplained light phenomena because it's predictable, observable, and scientifically studied rather than dismissed. Researchers have measured the light's electromagnetic signatures, thermal profiles, and movement patterns, confirming they're real physical objects generating measurable energy, not atmospheric reflections or optical illusions. Proposed explanations range from piezoelectric effects in the valley's geology creating plasma balls, to combustion of scandium dust particles, to exotic atmospheric chemistry involving radon gas and ionized aerosols. None of these fully account for the light's behavior, the way they seem to respond to observers, the structured movement patterns, the ability to appear regardless of weather conditions. The valley has become a natural laboratory for studying rare atmospheric phenomena, yet after decades of systematic observation, we have detailed data about what happens and almost no consensus on why. Level 24. Why? We hiccup. That involuntary spasm of your diaphragm, the sharp intake of breath interrupted by your glottis snapping shut with an audible hic sound, serves no apparent purpose in adult human physiology. Yet it's a reflex so deeply embedded in your nervous system that it can persist for days or years in extreme cases. The longest recorded case of continuous hiccups lasted 68 years, suggesting the underlying mechanism is remarkably robust even when malfunctioning. Most researchers believe hiccups are a vestigial reflex left over from our amphibian ancestors. Tadpoles use a similar breathing pattern to switch between using gills and lungs, coordinating diaphragm contractions with glottis closures to prevent water from entering their lungs while gulping air at the surface. In humans, this ancient breathing program occasionally activates inappropriately, triggered by eating too fast, drinking carbonated beverages, sudden temperature changes, or emotional stress. This evolutionary relic theory explains why the reflex exists, but doesn't explain why it persists across all mammals, why it's harder to suppress than other vestigial reflexes, or why the triggers are so varied and seemingly random. Level 25. The Fermi paradox. The universe is 13.8 billion years old. contains an estimated 200 billion trillion stars, and follows physical laws that make life's emergence seem inevitable given enough time and suitable conditions. Yet, we've detected no confirmed signals from alien civilizations. No megastructures. No von Neumann probes. No evidence whatsoever that intelligence exists anywhere except on this single planet. This is the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" during a casual lunch conversation in 1950. And it's arguably the most troubling silence in science. The math suggests Earth should be late to the party. Thousands of civilizations should have emerged in our galaxy alone, some millions of years older than us, easily capable of colonizing the entire Milky Way. Proposed solutions fall into three categories. Life is extraordinarily rare. Intelligence inevitably self-destructs. Or advanced civilizations exist but remain invisible for reasons we can't comprehend. Each explanation is profoundly unsettling in different ways, and we have no data to distinguish between them, making this less a scientific mystery and more an epistemological crisis where every possible answer challenges our assumptions about existence. Rest break. Pause here for a moment. Let these questions settle. Notice what you're already seeing differently. How many everyday mysteries you've never questioned? How many answers we thought we had that turned out to be incomplete? If any of these have shifted how you see the world, subscribe so you don't miss what comes next. There's a lot more ahead tonight. What follows goes deeper, from familiar enigmas to patterns that break common sense. Stay with me. Level 26. The Pioneer Anomaly. When NASA's Pioneer 10 and 11 spacecraft drifted past Neptune in the 1980s, still transmitting data from the edge of the solar system, mission controllers noticed something wrong. Both probes were slowing down slightly more than gravitational calculations predicted, decelerating at approximately 8.74 times 10 to the power of minus 10 meters per second squared. A tiny discrepancy that shouldn't exist according to our models of orbital mechanics. The anomaly was consistent, measurable, and completely unexpected, persisting over decades as the spacecraft traveled billions of miles into interplanetary space. Every conventional explanation was tested and eliminated. Solar radiation pressure didn't match the magnitude. Gravitational influence from unknown Kuiper belt objects was too weak. Fuel leaks were ruled out by thermal models. For years, some physicists wondered if we were seeing evidence of modified gravity at extreme distances, a breakdown in Newton's laws that might explain dark matter. The eventual solution turned out to be mundane: anisotropic thermal radiation, heat from the spacecraft's power source pushing slightly harder in one direction than others. But arriving at this answer required analyzing engineering blueprints and modeling heat distribution across decades-old hardware. Level 27. Fast radio bursts. In 2007, astronomers reviewing archival data from the Parkes radio telescope noticed a signal that should have been impossible. A burst of radio waves lasting less than 5 milliseconds, containing as much energy as the sun emits in an entire day, originating from billions of light years away. The signal was so brief and powerful that it seemed like an instrumental glitch, except the pattern matched theoretical predictions for what an astrophysical event would look like if something could release enormous energy in milliseconds at cosmological distances. For 6 years, this remained a curiosity, a single anomalous detection that might have been real or noise. Then, additional bursts were detected, different locations, different intensities, but the same impossibly brief duration and enormous energy. We now know these fast radio bursts happen thousands of times per day across the observable universe, making them common astronomical events we simply weren't looking for. What produces them remains unknown. Theories range from magnator starquakes to colliding neutron stars to evaporating black holes, each explaining some observed properties while failing to account for others, and none explaining why a subset of FRBs repeat while most appear only once. Level 28. The WOW signal. On August 15, 1977, at 11:16 p.m. Eastern Time, the Big Ear Radio Telescope in Ohio detected a narrowband radio signal at 1420 MHz. The emission frequency of neutral hydrogen, considered the most likely channel for interstellar communication, because any civilization studying the universe would know to look there. The signal was strong, narrowly focused, rose and fell over 72 seconds exactly as expected for a source tracked across the sky by Earth's rotation, and came from the direction of Sagittarius near the constellation's densest star fields. Astronomer Jerry Amon, reviewing the data printout days later, was so struck by its characteristics that he circled it and wrote "Wow" in the margin, giving the signal its name. It has never repeated. Follow-up observations of the same region, conducted with more sensitive equipment over the following decades, detected nothing. The signal's frequency, duration, intensity, and behavior matched theoretical predictions for an artificial transmission from deep space, yet it appeared once and vanished. Natural explanations, cometary hydrogen clouds, reflected satellite signals, all have problems matching the signal's characteristics, but so does the extraterrestrial hypothesis when confronted with the silence that followed. Level 29. Quantum tunneling time. When a particle encounters an energy barrier it shouldn't be able to cross, quantum mechanics predicts it has some probability of appearing on the other side anyway, a phenomenon called tunneling, verified in countless experiments, responsible for radioactive decay, crucial to semiconductor function, fundamentally weird but thoroughly documented. What nobody can agree on is how long the tunneling process takes. Does the particle spend time inside the barrier? Does it teleport instantaneously? Does the question even make sense in quantum terms? Experiments designed to measure tunneling time produce contradictory results depending on methodology. Some suggest tunneling is instantaneous, implying faster-than-light information transfer and violating relativity. Others measure finite traversal time consistent with light speed limits, but raise questions about what the particle is doing inside a region where it doesn't have enough energy to exist. Theoretical physicists have published hundreds of papers offering different interpretations. Tunneling time is real. Tunneling time is meaningless. Tunneling time depends on how you define measurement. And the fact that we can't answer this basic question about a ubiquitous quantum process reveals how little we understand about what actually happens during quantum events when we're not observing them. Level 30. The Flyby Anomaly. When spacecraft perform gravity-assist maneuvers around Earth, using the planet's gravitational field to alter trajectory and gain velocity, they sometimes pick up slightly more speed than orbital mechanics predicts, an effect measured with extreme precision using Doppler shift in their radio signals. The Near spacecraft in 1998 gained an extra 13 millimeters per second. Rosetta in 2005 showed anomalous acceleration. Juno in 2013 exhibited unexplained velocity change. The effect is tiny, only detectable because we can measure spacecraft velocities to millimeter per second accuracy. But it's real. reproducible, and unexplained by conventional physics. Every standard correction has been applied. Atmospheric drag, solar radiation pressure, tidal effects, relativistic corrections, Earth's oblateness, and the anomaly persists. Some flybys show the effect, others don't, with no clear pattern determining when it appears. Proposed explanations range from dark matter halos around Earth to modifications of general relativity at planetary scales to unmodeled rotational effects from Earth's motion, but none fully match the observational data. The anomaly sits in that frustrating space where it's too small to motivate major theoretical revision, but too consistent to dismiss as instrumental error. A hint that something in our understanding of orbital mechanics is incomplete. Level 31. Sonoluminescence. When you take a small glass flask of water, introduce a sound wave at the right frequency, and create a tiny cavitation bubble, a void in the liquid where pressure drops below vapor pressure, something extraordinary happens. The bubble collapses with such violence that it emits a flash of light, converting acoustic energy into photons through a process that shouldn't be possible under conventional physics. The light flash lasts only picoseconds. The bubble collapses so rapidly that temperatures inside briefly reach 20,000 Kelvin, hotter than the sun's surface. Yet the surrounding water remains room temperature, implying heat concentration and energy density that violate basic thermodynamic expectations. This phenomenon was discovered in 1934 and has been studied intensively for 9 decades. Yet we still don't have a complete theory explaining how sound creates light. Partial explanations involve shockwave compression, plasma formation, and quantum vacuum radiation, but none fully account for the energy conversion efficiency, the spectral characteristics of the emitted light, or why certain liquids produce stronger sonoluminescence than others. The effect is reproducible, measurable, and completely routine in laboratories worldwide. A textbook example of something we can control without understanding. Level 32. The electron radius problem. Electrons appear to be point particles, mathematical objects with zero spatial extent, no internal structure, no measurable size. Yet they carry charge, mass, and spin, properties that seem to require some physical extension to exist in the first place. When you try to calculate the electron's classical radius based on its mass and charge, you get approximately 2.8 times 10 to the power of minus 15 meters. But quantum field theory treats electrons as point-like, with radius effectively zero, creating a fundamental inconsistency between classical and quantum descriptions that nobody has resolved. The problem deepens when you consider electron scattering experiments. Fire electrons at each other or at other particles. Measure how they deflect, and the results show no deviation from point particle behavior down to distances of 10 to the power of minus 18 meters, 3 orders of magnitude smaller than the classical radius calculation suggests. This implies either electrons truly have zero size, raising questions about how dimensionless points possess properties, or they have structure at scales we cannot yet probe, or the question itself is malformed because quantum objects don't have definite positions until measured. All 3 possibilities challenge foundational assumptions about what particles are. Level 33. The lithium problem. Big Bang nucleosynthesis, the process that created the first atomic nuclei in the early universe, makes precise predictions about the abundance of light elements produced in the first few minutes after the universe began. And for hydrogen, helium-4, and deuterium, observations match predictions almost perfectly, confirming our models work. Lithium-7 is the exception. Theory predicts the universe should contain roughly 3 times more lithium-7 than we actually observe in the oldest stars, creating a discrepancy that has persisted for over 4 decades, despite increasingly precise measurements. Every attempt to resolve the mismatch has failed. Maybe stars destroy lithium through internal processes, but calculations show they don't destroy enough. Maybe lithium settles toward stellar cores faster than expected, but observational evidence doesn't support this. Maybe the Big Bang physics was slightly different than we think, but changing the parameters enough to fix lithium breaks the successful predictions for other elements. The lithium shortfall suggests either our understanding of stellar evolution is wrong, our understanding of Big Bang conditions is wrong, or some unknown physics was operating in the early universe that selectively affected one element while leaving the others untouched. Level 34. Rotating detonation engines. Take a hollow cylinder, inject fuel and oxidizer. Ignite a detonation wave that travels around the ring faster than sound, and you create a propulsion system that should, according to standard thermodynamic analysis, be less efficient than conventional rocket engines, because detonations are violent, chaotic, and waste energy. Yet, when actually built and tested, rotating detonation engines outperform traditional designs by 10 to 15%, producing more thrust per unit of fuel despite violating the theoretical predictions. The detonation wave continuously chases itself around the cylinder at supersonic speeds, creating a self-sustaining combustion pattern that somehow extracts more useful work from the same chemical energy than steady-state burning achieves. Engineers have demonstrated working prototypes, measured the performance gains, confirmed they're real and reproducible. Yet the theoretical explanation for why they work better remains incomplete. Computational fluid dynamics simulations can reproduce the behavior but don't explain the underlying principle. Something about the unsteady, shock-driven combustion process accesses thermodynamic pathways that equilibrium analysis misses, pointing toward gaps in how we model high-speed reacting flows, a case where building the thing was easier than understanding why it works. Level 35. The proton radius puzzle. Measuring the proton's radius should be straightforward. Scatter electrons off protons. Measure the deflection angles. Extract the charge distribution. Done. And for decades, experiments using electron scattering consistently yielded a radius of approximately 0.877 femtometers. Then, in 2010, researchers measured the proton radius using muonic hydrogen. Hydrogen atoms, where the electron is replaced by a muon, a heavier cousin that orbits 200 times closer to the nucleus, and got a result of 0.84 femtometers, about 4% smaller. This sounds like a minor discrepancy until you realize it's 7 standard deviations away from the electron scattering value. Meaning, if both measurements are correct, there's less than 1 in a trillion chance this is statistical noise. Either one experimental method is systematically wrong in ways nobody can identify, or the proton appears smaller when probed by muons than when probed by electrons, implying physics beyond the standard model where particle interactions vary depending on what's doing the measuring. Subsequent experiments have produced conflicting results, some supporting the smaller radius, others the larger, and a decade later, we still don't know the actual size of one of the universe's most fundamental particles. Level 36. Ultra-high energy cosmic rays. Occasionally, particles from space strike Earth's atmosphere with kinetic energies exceeding 10 to the power of 20 electron volts. Energies so high that a single subatomic particle carries the kinetic energy of a baseball thrown at 60 miles per hour, violating theoretical limits on how much energy particles can retain while crossing cosmic distances. The problem is the GZK cutoff. Any particle with energy above 5 times 10 to the power of 19 electron volts traveling through intergalactic space should collide with cosmic microwave background photons, losing energy until it drops below the cutoff, meaning particles above this threshold can only travel a few 100 million light-years before degrading. Yet we detect ultra-high-energy cosmic rays regularly, and their arrival directions don't point to any obvious nearby sources within the GZK radius. Either these particles are being created by astrophysical processes far more powerful than anything we've identified. Magnetars, active galactic nuclei, gamma-ray bursts operating at energies we've never directly observed. Or they're traveling farther than they should be able to, suggesting new physics that violates the assumptions behind the GZK cutoff. Or they're not particles at all, but some other phenomenon we're misinterpreting as high-energy radiation. Level 37. The Antarctica Neutrino. Anomaly. Deep in the Antarctic ice, the ice cube neutrino detector, a cubic kilometer of frozen water instrumented with thousands of sensors, occasionally detects neutrinos traveling upward through the Earth, entering from the opposite side after passing through thousands of miles of solid rock. This is expected. Neutrinos barely interact with matter and can traverse entire planets. What's not expected is the anomalous excess of high-energy upward-traveling events that don't match standard neutrino physics. These events have energies and arrival angles suggesting they're produced by cosmic ray interactions in the atmosphere on the far side of Earth. But the particle flux at these energies is higher than atmospheric models predict, and the events sometimes show unusual characteristics. Too much energy, wrong interaction signatures, spatial clustering that shouldn't occur if they're random. Proposed explanations range from tau neutrino oscillations behaving differently than expected, to sterile neutrino production, to exotic physics beyond the standard model, but several years of data haven't converged on a definitive answer, leaving open the possibility we're seeing either atmospheric physics we don't fully understand, or the first hints of new neutrino properties. Level 38. Quantum Darwinism. The quantum world operates under superposition. Particles exist in multiple states simultaneously until measured, while the classical world contains definite states. The cat is either alive or dead. The particle is in one location. How quantum indefiniteness becomes classical definiteness is the measurement problem. And while decoherence explains how superpositions get washed out by environmental interactions, it doesn't explain why multiple observers agree on measurements, why outcomes are stable and reproducible, or why certain properties become classical while others remain quantum. Quantum Darwinism proposes that only specific quantum information survives interaction with the environment. Information that gets redundantly imprinted across many environmental degrees of freedom, like a signal broadcast through multiple channels, while fragile superposition states get destroyed, creating natural selection of classical properties. This explains why you and I both see the same electron position. We're both reading copies of information that survived environmental scrutiny. The theory is mathematically elegant and matches experimental observations in controlled systems, but it doesn't explain why nature selects these particular observables to become classical, or what the environment means in a closed quantum universe where everything is entangled. Level 39. The galaxy rotation problem. When you measure how fast stars orbit the center of a spiral galaxy, Newtonian mechanics makes a clear prediction. stars closer to the galactic core should orbit faster than stars farther out. The same way, inner planets orbit the Sun faster than outer planets, with velocity decreasing proportionally to distance. But when astronomers measured galactic rotation curves in the 1970s, they found something impossible. Stars at the galaxy's edge orbit just as fast as stars near the center, producing flat rotation curves that shouldn't exist under visible matter alone. Either galaxies contain roughly 5 times more mass than we can see, dark matter forming invisible halos extending far beyond the visible disk, or gravity behaves differently on galactic scales than Newton's laws predict. Dark matter is the mainstream explanation, supported by gravitational lensing, cosmic microwave background measurements, and large-scale structure formation. Yet, despite decades of searching, we've never directly detected a dark matter particle, making this either the universe's most abundant substance that happens to be invisible, or evidence that our gravitational theories fail at scales larger than solar systems. Level 40. The CMB cold spot, the cosmic microwave background, the afterglow of the Big Bang, visible in every direction as microwave radiation at 2.7 Kelvin, should be statistically uniform, showing random temperature fluctuations with no preferred patterns when you map the entire sky. Except there's a region in the constellation Eridanus, roughly 10 degrees across, where the temperature is about 70 microkelvins colder than average, a deviation that should occur by random chance in less than 2% of universes. This cold spot was first detected in 2004 and has been confirmed by multiple satellite observations, ruling out instrumental error. Proposed explanations include a supervoid, an unusually large empty region of space between us and the CMB, causing photons to lose more energy than normal. But even the largest supervoids can't fully account for the temperature deficit. More exotic theories invoke cosmic texture defects, bubble collisions from eternal inflation, or statistical flukes. The troubling aspect is not that the cold spot exists, but that it sits right at the edge of statistical significance, making it impossible to determine whether we're seeing meaningful new physics or just the kind of random outlier that inevitably appears when analyzing enough data. Level 41. The axis of evil. When cosmologists map the cosmic microwave background, the universe's oldest light, showing temperature variations from 13.8 billion years ago, they expect to find patterns that are statistically random, isotropic, with no preferred direction or orientation in space. Instead, they discovered something disturbing. The largest temperature fluctuations align along a single axis, creating a cosmic spine that stretches across the entire observable universe, pointing in a direction that shouldn't be special. This alignment persists across multiple angular scales, meaning it's not just one anomalous feature, but a systematic orientation in the fundamental structure of space-time itself. The phenomenon earned the nickname Axis of Evil from cosmologist João Magalhães, because it seems to violate the Copernican principle, the foundational assumption that our location and orientation in the universe should be unremarkable. Possible explanations include statistical flukes, residual contamination from our galaxy despite correction attempts, or genuine large-scale anisotropy in the universe's expansion. If the alignment is real, it suggests either our cosmological models are wrong, our position in the universe is special in ways that challenge fundamental principles, or we're seeing artifacts of physics that operated before. Inflation homogenized the early universe. Level 42. Ball Lightning Laboratory. Failure. Scientists have attempted to recreate ball lightning in controlled conditions for over a century, using high-voltage electrodes, microwave cavities, chemical combustion, plasma torches, and every conceivable energy source that might generate luminous spheres. Yet no laboratory experiment has successfully produced anything matching the natural phenomenon's key characteristics simultaneously. Several seconds of duration, ability to pass through solid barriers, silent or hissing sound, varied colors, explosive termination. You can create plasma balls that last milliseconds, glowing orbs that stay stationary, chemical reactions that produce light but no motion. Every experiment captures one or two features while missing the others. The most promising recent work involves vaporizing silicon with electrical arcs, creating glowing silicon vapor balls that persist for seconds. But these don't pass through windows or move against air currents the way eyewitness accounts describe. This failure to recreate ball lightning, despite knowing roughly what ingredients should be involved, atmospheric electricity, aerosols, chemical energy, suggests we're missing either a critical component or a specific arrangement of conditions that nature achieves during thunderstorms, but laboratories cannot reproduce. The phenomenon exists in the frustrating gap between well-documented reality and laboratory verification. Level 43. The Muon G. 2. Anomaly. The muon, essentially a heavy electron, has a magnetic moment that quantum electrodynamics predicts with extraordinary precision, calculating contributions from virtual particle interactions, vacuum fluctuations, and quantum corrections out to 11 decimal places. When physicists measured the actual muon magnetic moment in 2021 using particle accelerators at Fermilab, they found a value that differs from theoretical prediction by about 0.000000000025, a discrepancy that sounds negligible until you realize this measurement is precise enough to detect differences at the level of 1 part in 10 billion, and the disagreement sits at 4.2 standard deviations, meaning there's roughly a 1 in 40,000 chance this is statistical noise. Either the standard model's quantum corrections are incomplete, missing contributions from unknown particles, or forces that slightly alter the muon's properties, or our calculations contain subtle errors that compound across the many decimal places, or experimental systematic uncertainties are larger than estimated. This tiny mismatch could be the first confirmed evidence of physics beyond the standard model. New particles, new forces, new fields, or it could evaporate with better measurements. But for now it stands as one of the most precise disagreements between theory and experiment in all of physics. Level 44. Pulsating. Aurora. Occasionally, the aurora borealis doesn't flow in curtains or waves, but pulses. Sections of the sky flash on and off in synchronized patterns, brightening and dimming with periods of a few seconds, creating coordinated light shows across hundreds of miles that look less like natural phenomena and more like something deliberately switching on and off. These pulsating auroras correlate with chorus waves, electromagnetic oscillations in Earth's magnetosphere that occur in discrete bursts, suggesting the pulsations happen when electrons from the Van Allen radiation belts rain down into the atmosphere in rhythmic packets triggered by wave-particle interactions in space. What researchers cannot explain is the synchronization mechanism, how electrons across vast regions of the magnetosphere respond to chorus waves in perfect unison, creating simultaneous auroral pulses that span continental distances. Computer simulations can reproduce individual electron trajectories responding to waves, but struggle to generate the observed large-scale coordination without invoking unexplained organization in the magnetosphere. Recent satellite data shows that chorus wave packets organize into structured bursts, but this just pushes the mystery back one level. What organizes the waves themselves? And why does this organization only happen during certain geomagnetic conditions? Level 45. The Hubble tension. The universe is expanding, and measuring the rate of that expansion, called the Hubble constant, should yield the same value regardless of measurement method, assuming our cosmological model is correct. Except it doesn't. When you measure the Hubble constant using nearby objects, observing Cepheid variable stars and supernovae in relatively close galaxies, you get approximately 73 kilometers per second per megaparsec. When you measure it using the cosmic microwave background, analyzing the universe as it appeared 380,000 years after the Big Bang and extrapolating forward, you get 67. Both measurements are extremely precise, refined through decades of increasingly careful observation, yet they disagree by about 9%, and the discrepancy has grown more significant as measurement precision improved. This is called the Hubble tension, and it's not just a technical disagreement. If both measurements are correct, it means either our understanding of how the universe evolved is wrong. Unknown physics operated in the early universe. Dark energy behaves differently than we think, or systematic errors plague one measurement method in ways nobody can identify. Every attempt to resolve the tension has failed, leaving us with two incompatible answers to the same fundamental question. Level 46. Quantum coherence in biology. Photosynthesis converts light into chemical energy with near-perfect efficiency. Over 95% of absorbed photons generate useful chemistry, a performance level that shouldn't be possible using classical physics alone, where energy transfer inevitably loses significant amounts to heat and disorder. In 2007, researchers discovered that photosynthetic complexes maintain quantum coherence, wave-like superposition states where energy simultaneously explores multiple pathways, for hundreds of femtoseconds at biological temperatures, far longer than quantum mechanics predicts for warm, wet, noisy environments. This quantum coherence allows the system to sample all possible energy transfer routes simultaneously and select the most efficient path, achieving performance that classical molecules cannot match. The discovery challenged the assumption that quantum effects wash out instantly in biological systems, opening questions about whether evolution has learned to exploit quantum mechanics for computational advantages. Since then, quantum effects have been proposed in bird navigation, enzyme catalysis, and olfaction, though most remain controversial. The core mystery isn't whether biology uses quantum mechanics. All chemistry is fundamentally quantum. But whether evolution has specifically engineered systems that preserve quantum coherence for functional advantages. And if so, how molecular machinery protects fragile quantum states from environmental destruction. Level 47. The Eemian interglacial sea level. Roughly 125,000 years ago, during the last interglacial period before the most recent ice age, Earth's temperature was approximately 1 to 2 degrees Celsius warmer than today, comparable to current projections for near-future warming. Yet geological evidence shows sea levels were 6 to 9 meters higher than present, requiring massive ice sheet collapse from Greenland, West Antarctica, or both. This creates a troubling puzzle. Current climate models, when run with Eemian temperature conditions, don't predict enough ice loss to generate 6 to 9 meter sea level rise. suggesting either the models underestimate ice sheet vulnerability to warming or some other mechanism beyond temperature alone drove the collapse. Coral reef terraces, beach deposits, and fossil shorelines from the Eemian period are found well above current sea level on coastlines worldwide, providing clear evidence that the high sea levels were real and sustained. The implications are uncomfortable. If ice sheets can collapse rapidly enough to raise sea level 6+ meters under conditions only slightly warmer than today, current projections for 21st century sea level rise might be dramatically underestimating the risk, or the Eemian involved specific conditions we don't yet understand. Level 48. Rogue waves. For centuries, sailors reported encounters with solitary waves that appeared without warning in open ocean. Sheer walls of water 20 to 30 meters high, rising suddenly from moderate seas, far larger than surrounding waves, lasting only seconds before dissipating. And oceanographers dismissed these accounts as exaggerations or misidentifications. Then, on January 1st, 1995, the Draupner oil platform in the North Sea recorded a wave measuring 25.6 meters from trough to crest in seas, where significant wave height was only 12 meters, providing instrumental confirmation that rogue waves exist and violate standard ocean wave statistics. These waves are not simply the tallest in a distribution. They're statistical outliers that shouldn't occur based on linear wave theory, forming through mechanisms that remain incompletely understood. Current explanations invoke nonlinear wave interactions, crossing seas from different storm systems, focusing energy, wave current interactions, modulational instability causing nearby waves to merge. But predicting when and where rogue waves form remains impossible, and their frequency exceeds what probability models predict, suggesting either the underlying wave physics contains nonlinear effects we haven't fully characterized, or ocean conditions create wave-focusing phenomena more often than random chance allows. Level 49. The Faint Young Sun. Paradox. 4 billion years ago, when life first emerged on Earth, the sun was approximately 30% dimmer than today, a consequence of stellar evolution, as stars brighten gradually over time as they convert hydrogen to helium. With 70% of current solar output, Earth's surface temperature should have been well below freezing. The oceans should have been solid ice, and liquid water, necessary for life's origin, should not have existed. Yet geological evidence overwhelmingly shows that early Earth had liquid oceans. Sedimentary rocks from 3.8 billion years ago formed in water. Isotopic signatures indicate water-based chemical weathering. Stromatolites appear in ancient rocks, all pointing to a warm, wet planet despite insufficient solar heating. Something kept early Earth warm when it should have been frozen. Proposed solutions include higher concentrations of greenhouse gases, particularly methane produced by early life and carbon dioxide from volcanic outgassing. But atmospheric models struggle to generate enough warming without creating other problems. Too much CO2 forms carbonate minerals. Too much methane gets destroyed by UV radiation. Alternative explanations invoke different planetary albedo, or early Earth's rotation creating different atmospheric circulation, but none fully resolves the paradox. Level 50. Fast ice sheet collapse. Ice core records from Greenland reveal that approximately 11,700 years ago, at the end of the last ice age, the climate shifted from glacial to interglacial conditions in less than a decade. Temperature increased by 10 degrees Celsius, precipitation doubled, atmospheric circulation reorganized, and massive ice sheets that had covered continents for 100,000 years began rapidly collapsing. The standard view of ice ages portrays gradual transitions over thousands of years, but the paleoclimate record shows abrupt jumps, suggesting Earth's climate system has tipping points, where feedback loops amplify small changes into catastrophic reorganizations. During one event, the Younger Dryas transition, Greenland warmed by approximately 10 degrees Celsius in 50 years, implying ice sheets can disintegrate far faster than contemporary models predict. The mechanisms remain debated. Did sudden freshwater release from glacial lakes shut down ocean circulation? Did ice shelf collapse remove backstop pressure, allowing land ice to flow faster into the ocean? The unsettling implication is that ice sheets might be far more sensitive to warming than current projections assume, capable of transitioning from stable to collapsing in decades rather than centuries, making sea level rise predictions potentially catastrophic underestimates. Rest break. You've come a long way, 50 mysteries down, from why we yawn and why we dream to spacecraft anomalies and signals from deep space that refuse to repeat. You started with the familiar, the everyday questions hiding in plain sight. Things you've experienced but never questioned. Then you moved into the edge cases, the phenomena that shouldn't exist according to what we know but stubbornly persist anyway. Anomalies that break the rules, patterns that resist explanation, measurements that point to something missing in our understanding of how the universe works. What comes next is different. The next 25 levels shift into something quieter, more unsettling. Not the drama of unexplained signals or missing energy, but the eerie precision of constants that have to be exactly what they are. Numbers fine-tuned to impossible accuracy. Coincidences so improbable they feel designed. The universe balanced on razor-thin margins that shouldn't work but do. You'll encounter values that can't vary by more than a fraction of a percent without making stars impossible, life impossible, chemistry impossible, matter itself impossible. The fine structure constant at exactly 1/137. The cosmological constant, smaller than theory, predicts by 120 orders of magnitude. The Higgs mass sitting at precisely the value that keeps the vacuum from collapsing. These aren't stories or speculation. They're measured facts, confirmed by experiments across decades, and nobody knows why they have the values they do, or what happens if you try to change them. This isn't about fear, it's about wonder. The numbers aren't threatening. They're invitations to see how delicate the structure of reality actually is. How many things could have gone differently, but didn't. There's beauty in that fragility, in the realization that existence itself walks a tightrope across an abyss of impossible configurations. And somehow we ended up in the one narrow path where matter can form. Stars can shine, atoms can bond, and observers can exist to wonder why. The mysteries ahead are quieter than the ones behind you. Less about missing spacecraft or unexplained signals, more about the foundation itself, why the numbers work, why the constants balance, why anything exists instead of nothing. If you've made it this far, you're not a casual listener. Subscribe if you haven't already. This is where it starts getting really interesting. The mysteries ahead don't ask what happened. They ask, why is it possible at all? Take a breath. Let the first 50 settle. When you're ready, the next 25 are waiting. Mysteries written into the fabric of physics itself. Constants and coincidences that keep cosmologists awake at night wondering how reality manages to exist at all. Level 51. The fine structure constant. There's a number woven into the fabric of reality, approximately 1 over 137.036, that governs how strongly electrons interact with photons, determines the strength of electromagnetic force, controls atomic energy levels, and shows up in every calculation involving light and matter. This is the fine structure constant, usually denoted alpha, and it's one of physics' most fundamental dimensionless numbers, meaning it's the same regardless of what units you measure in. A pure ratio that describes something essential about how the universe operates. Nobody knows why it has this value. You can measure alpha to 10 decimal places, but you cannot derive it from first principles, cannot calculate it from deeper theory, cannot explain why it's 1 over 137 instead of 1 over 100 or 1 over 200. Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that all good theoretical physicists worry about but cannot explain. If alpha were even slightly different, 5% larger or smaller, atoms would not form stable structures, chemistry would not work, stars would not produce the elements necessary for life, making this arbitrary-seeming number precise to a degree that determines whether complex matter can exist. Level 52. The cosmological constant problem. When you calculate the energy density of empty space using quantum field theory, summing up contributions from all virtual particles constantly popping in and out of existence in the quantum vacuum, you get a prediction for how strongly dark energy should accelerate the universe's expansion. The calculation is straightforward. The physics is well established, and the answer comes out wrong by a factor of 10 to the power of 120. Not 10%, not double, but one followed by 120 zeros, making this the worst theoretical prediction in the history of physics. Observations show the cosmological constant has a tiny positive value, barely enough to cause the universe's accelerating expansion, while quantum mechanics predicts a value so enormous that the universe should have exploded apart instantly after the Big Bang. Something is canceling out the vacuum energy with absurd precision, getting rid of 120 decimal places worth of contribution while leaving just enough to cause cosmic acceleration. Either quantum field theory catastrophically fails when applied to gravity, or there's a fine-tuning mechanism operating at precision levels that make winning the lottery look inevitable. Or we're fundamentally misunderstanding what vacuum energy means in a gravitational context. Level 53. The hierarchy problem. Gravity is 10 to the power of 36 times weaker than electromagnetism. So much weaker that a refrigerator magnet can overcome Earth's entire gravitational pull on a paperclip. So much weaker that you can jump off the ground despite a planet's mass pulling you down. This enormous gap between gravitational strength and other forces is called the hierarchy problem, and nobody knows why it exists. In quantum field theory, the Higgs boson mass, which sets the scale of electroweak interactions, should receive huge quantum corrections from virtual particles at high energies, pushing it up toward the Planck scale where gravity becomes strong. Yet somehow all these contributions cancel out to 35 decimal places, leaving the Higgs at exactly 125 giga-electronvolts. This kind of fine-tuning suggests either new physics at accessible energy scales, preventing the runaway corrections, or the standard model is incomplete in ways that make gravity naturally weak. Or we live in a universe selected from countless possibilities, specifically because it has this precise mass ratio. Each explanation requires physics beyond what we've observed. Yet the alternative is accepting that fundamental constants are fine-tuned to arbitrary precision for no deeper reason. Level 54. baryon asymmetry. The universe contains matter but not antimatter. Stars are made of protons and neutrons, not antiprotons and antineutrons. Planets are made of atoms, not antiatoms. You are made of particles, not antiparticles. And this asymmetry should not exist. The Standard Model predicts that the Big Bang produced equal amounts of matter and antimatter, which should have annihilated completely, leaving a universe containing only photons, no atoms, no structure, no you. Yet, for every billion matter-antimatter pairs that annihilated in the early universe, one extra matter particle survived, creating the 1,000,000,000-to-1 ratio between photons and baryons we observe in the cosmic microwave background, and allowing matter to condense into galaxies. Where did this asymmetry come from? The Standard Model includes CP violation, physics that treats matter and antimatter slightly differently, but the magnitude is orders of magnitude too small to explain the observed baryon excess. Either unknown physics operated in the first microsecond after the Big Bang, generating matter-antimatter asymmetry through mechanisms we haven't discovered, or the universe started with initial conditions that slightly favored matter for no fundamental reason, or we're missing something about how symmetry breaking worked in the early universe. Level 55. The electron mass. The electron weighs 0.511 mega-electron volts, a specific value that determines atomic size, chemical bond strength, the energy required to ionize atoms, and essentially all of chemistry and biochemistry. Nobody knows why it has this mass. In the Standard Model, particle masses arise from interactions with the Higgs field. But the strength of those interactions, the Yukawa couplings, are free parameters that must be measured rather than calculated, meaning the electron mass is an input to the theory, not a prediction from it. The electron is roughly 200 times lighter than the muon, its heavier cousin, and 3,500 times lighter than the tau lepton, creating a mass hierarchy with no theoretical explanation. If the electron were 1% heavier, chemical bonds would form differently. Molecules would have different energies. Biochemistry would not work the same way, potentially preventing life. If it were 10% heavier, stellar fusion would proceed differently, changing how stars produce elements. The precise value sits in a narrow window that allows complex chemistry, but we have no theory explaining why nature selected this particular mass from the infinite possible values the Higgs mechanism permits. Level 56. The strong CP problem. Quantum chromodynamics, the theory describing how quarks bind together into protons and neutrons, contains a term that allows CP violation, meaning interactions that distinguish between matter and antimatter, particles and antiparticles. This term is characterized by a parameter called theta, which can theoretically range from 0 to 2 pi, with different values producing different amounts of CP violation in strong interactions. Experiments measuring the neutron's electric dipole moment, a signature of CP violation, place constraints showing theta must be smaller than 10 to the power of minus 10, essentially 0. This is bizarre. Why would a free parameter in our most fundamental theory of matter happen to be tuned to 10 decimal places of precision? Either theta is exactly 0 for some deep symmetry reason we haven't discovered, or an unknown mechanism drives it toward 0 dynamically. Or we live in a universe where this parameter just happens to be extraordinarily small by coincidence. The most popular solution, the axion, a hypothetical particle that would naturally drive theta to 0, has never been detected despite decades of searching. leaving the strong CP problem as a glaring fine-tuning in the standard model that no one can explain without invoking new physics. Level 57. The flatness problem. The universe appears to be geometrically flat. Parallel lines never converge or diverge. The angles of triangles sum to exactly 180 degrees on cosmic scales, to a precision better than 1%. This flatness requires the universe's total energy density to match the critical density needed to balance expansion against gravitational collapse with absurd accuracy. In the early universe, 1 second after the Big Bang, the density had to equal the critical value to better than 1 part in 10 to the 15th power, 15 decimal places, because any tiny deviation would have grown exponentially over time, either causing the universe to recollapse within seconds or expanding so fast that no structures could form. Why was the initial density tuned so precisely? Inflation theory, a brief period of exponential expansion in the first fraction of a second, solves this by driving the universe toward flatness regardless of initial conditions, flattening space-time the way stretching a balloon's surface makes it appear locally flat. But inflation itself requires fine-tuning. The inflattened field needs specific potential energy shape, specific initial conditions, specific coupling strengths, shifting the problem from why is the universe flat to why did inflation happen? Level 58. The coincidence problem. For most of cosmic history, the universe's energy was dominated by matter, the gravitational pull of galaxies slowing expansion, until approximately 4 billion years ago when dark energy became the dominant component, causing expansion to accelerate. This transition happened to occur right around the time intelligent observers evolved to measure it, creating a suspicious coincidence that seems too convenient to be random. If dark energy had dominated earlier, galaxies would not have formed, because accelerating expansion prevents matter from clumping together. If it had dominated later, we would observe a decelerating universe, and might never discover dark energy exists. The fact that we live in the brief cosmic era when matter and dark energy densities are comparable, within a factor of 2 despite spanning 80 orders of magnitude across cosmic history, suggests either anthropic selection, where observers can only exist during this narrow window, or tracking behavior, where dark energy's strength somehow depends on matter density, or pure coincidence. Each explanation requires physics beyond the standard model, yet observations provide no way to distinguish between them, leaving us with a fine-tuned cosmic timeline that seems designed for observers to witness the transition. Level 59. Neutrino mass ordering. Neutrinos come in 3 types: electron, muon, and tau, and quantum mechanics allows them to oscillate between types as they travel through space, a phenomenon verified by experiments that solve the solar neutrino problem and confirm neutrinos have mass. But we don't know the mass ordering. Are the masses arranged as m1 less than m2 less than m3 in a normal hierarchy similar to charged leptons? Or does m3 weigh less than m1 and m2 in an inverted hierarchy where the heaviest type is actually lightest? This isn't just a labeling issue. It affects everything from supernova dynamics to cosmological structure formation to whether neutrinos are their own antiparticles. Experiments measuring neutrino oscillations constrain the mass differences, but not the absolute ordering. And determining which hierarchy nature chose requires extremely difficult measurements of matter effects in oscillations or neutrinoless double beta decay that might never occur. The question seems simple: which neutrino is heaviest? But answering it requires understanding neutrino mass generation, a mechanism so different from how other particles get mass that it might involve physics completely outside the standard model, potentially connected to why the universe contains matter instead of antimatter. Level 60. The vacuum catastrophe. Empty space is not empty. Quantum field theory predicts that even in a perfect vacuum, particle-antiparticle pairs constantly fluctuate into existence, creating an energy density that should gravitate and curve spacetime. When you calculate this vacuum energy density by summing contributions from all quantum fields up to the Planck scale, you get a number around 10 to the power of 94 grams per cubic centimeter, a density so enormous that the universe should curve back on itself at scales smaller than an atom. Observations show the actual vacuum energy density is approximately 10 to the power of minus 26 grams per cubic centimeter, 120 orders of magnitude smaller than quantum field theory predicts, making this discrepancy the largest known gap between theory and experiment in physics. Either quantum field theory breaks down catastrophically when gravity is involved, or there's a cancellation mechanism removing 120 decimal places of vacuum energy while leaving a tiny residual that causes cosmic acceleration. Or the quantum vacuum doesn't gravitate the way we think it does. Every proposed solution requires new physics, modified gravity, or fine-tuning so extreme that it challenges whether we understand anything fundamental about quantum mechanics and spacetime. Level 61. Titius-Bode Law. In 1766, astronomer Johann Titius noticed a peculiar mathematical pattern in planetary orbits. If you take the sequence 0, 3, 6, 12, 24, 48, where each number doubles, add 4 to each term, then divide by 10. You get numbers that closely match the orbital distances of planets from the Sun in astronomical units. Mercury at 0.4, Venus at 0.7, Earth at 1.0, Mars at 1.6, the asteroid belt at 2.8, Jupiter at 5.2, Saturn at 10.0, all following this simple formula with eerie accuracy, despite having no theoretical justification. When Uranus was discovered in 1781, its orbit matched the next predicted position. Then Neptune was discovered in 1846, completely violating the sequence, and the pattern lost credibility. Yet the fact that 6 major bodies follow this arbitrary mathematical progression bothers astronomers because planetary formation theory provides no mechanism that would produce such spacing. Either it's pure coincidence that a simple geometric series matches orbits, or something about angular momentum distribution or gravitational resonances creates preferred orbital spacings that we haven't identified, leaving the Titius-Bode law as a pattern too consistent to ignore, but too theoretically unmotivated to trust. Level 62. The Chandrasekhar limit. When a star runs out of fuel and collapses under its own gravity, electron degeneracy pressure, quantum mechanical resistance arising from the Pauli exclusion principle, which prevents electrons from occupying the same quantum state, can halt the collapse, creating a stable white dwarf that will cool slowly over trillions of years. But this only works up to a specific mass. 1.4 solar masses, a threshold called the Chandrasekhar limit, above which electron degeneracy pressure cannot support the star and gravitational collapse continues, producing either a neutron star or black hole. This limit emerges from the interplay between general relativity and quantum mechanics, calculated by Subrahmanyan Chandrasekhar in 1930. What's remarkable is the precision, not approximately 1.4 solar masses, but 1.44 with tiny variations depending on composition, and the fact that this single number determines the fate of every star above a certain mass. If the limit were slightly higher, more stars would become white dwarfs, and the universe would contain fewer neutron stars and black holes. If it were lower, white dwarfs would be rare. The value emerges inevitably from fundamental constants, yet it sits precisely where it creates a balanced population of stellar endpoints. Level 63. Nuclear Binding Energy Curve. When you plot the binding energy per nucleon, how tightly nuclear particles are held together, across all elements from hydrogen to uranium, you get a curve that rises steeply, peaks sharply at iron 56, then gradually declines, creating a mountain shape with iron at the summit. This curve determines everything about nuclear physics. Lighter elements release energy through fusion, heavier elements through fission, and iron releases no energy either way, making it the most stable nucleus, the nuclear endpoint where stellar fusion stops. Stars can fuse hydrogen into helium, helium into carbon, continuing up the periodic table, each step releasing energy that keeps the star from collapsing. But when the core becomes iron, fusion becomes endothermic, energy production halts, and the star collapses into supernova within seconds. The fact that this binding energy curve peaks exactly at iron, element 26, atomic mass 56, rather than some lighter or heavier element, means that stellar evolution produces iron as waste product. Supernova scatter iron-rich material through space, and iron becomes the fourth most abundant element in Earth's crust. If the peak occurred elsewhere, the universe's chemical composition would be radically different. Level 64. The carbon-12 resonance. Carbon is essential for life. Organic chemistry, DNA, proteins, every biological molecule relies on carbon's unique ability to form 4 stable bonds. Yet carbon should barely exist in the universe. Stars produce carbon through the triple alpha process. 2 helium nuclei fuse into beryllium-8, which is unstable and decays in 10 to the power of minus 16 seconds. But if a third helium nucleus collides with the beryllium before it decays, it forms carbon-12. This requires an extraordinary coincidence. The carbon-12 nucleus must have an energy level at exactly the right energy to create resonance, amplifying the reaction rate by a factor of 1,000,000. Fred Hoyle predicted this resonance must exist in 1953, based purely on the fact that carbon is abundant, and experiments confirmed it. Carbon-12 has an excited state at 7.65 mega-electron volts, precisely where it needs to be. If this energy level were 4% higher or lower, the resonance wouldn't occur, carbon production would be 1,000 times less efficient, and the universe would contain almost no carbon. This is the Hoyle resonance, the most striking example of apparent fine-tuning in nuclear physics. A 0.4 mega-electron volt window determining whether carbon-based life can exist. Level 65. The deuteron binding energy. Deuterium, heavy hydrogen with 1 proton and 1 neutron, is the first step in stellar fusion, the gateway to all heavier elements, and the binding energy holding the deuteron together is approximately 2.2 mega-electron volts. This sounds arbitrary until you realize how precariously balanced it is. If the deuteron were bound just 0.06 mega-electron volts more tightly, about 3% stronger, deuterons, 2 protons bound together, would become stable, fundamentally altering stellar fusion because stars could bypass the slow proton-proton chain and fuse hydrogen directly. This would make stars burn hundreds of times faster. exhausting their fuel in millions of years rather than billions, giving life far less time to evolve. If the deuteron were bound 0.06 mega-electron volts less tightly, 3% weaker, it would be unstable, unable to form in stellar interiors, blocking the fusion chain and preventing helium production, stopping nucleosynthesis before it begins. The actual binding energy sits in a narrow window that allows stars to burn slowly enough to support long-term planetary stability while still producing elements necessary for chemistry. This 0.12 mega-electron-volt range represents roughly 5% of the deuteron binding energy, a precision that seems calibrated for life-supporting universe. Level 66, the water anomaly. Almost every substance becomes denser as it cools. Molecules pack more tightly as thermal motion decreases, but water violates this rule in a way that makes life on Earth possible. As water cools below 4 degrees Celsius, it begins expanding rather than contracting, becoming less dense, which is why ice floats instead of sinking, why lakes freeze from the top down, why aquatic life survives winter beneath protective ice layers. This anomalous behavior arises from hydrogen bonding. Water molecules form tetrahedral networks that create open crystal structures at low temperatures, but the detailed physics of why the density maximum occurs at exactly 4 degrees Celsius involves quantum mechanical effects in hydrogen bonds we still don't fully understand. If water's density maximum occurred at a different temperature, or if water behaved normally and became denser as it froze, ice would sink. Lakes and oceans would freeze solid from bottom up. Aquatic ecosystems would be impossible, and Earth's climate would be dramatically different. The precise temperature at which water reaches maximum density seems fine-tuned for life, yet emerges from molecular physics in ways that remain incompletely explained. Level 67. The speed of light. Light travels at exactly 299,792,458 meters per second in vacuum. Not approximately that speed, but exactly, because since 1983 the meter has been defined as the distance light travels in 1/299,792,458 of a second, making the speed of light a defined constant rather than measured quantity. But this raises a deeper question. Why does light travel at this speed rather than faster or slower? In special relativity, the speed of light is the maximum speed at which information can propagate through space-time, the cosmic speed limit that nothing with mass can reach and nothing without mass can avoid. You can measure it, define units around it, derive its value from electric and magnetic constants, but you cannot explain from first principles why it has this value. If light traveled faster, causality would operate differently, and relativistic effects would be weaker. If it traveled slower, time dilation and length contraction would be more extreme. The speed of light is woven into the structure of space-time itself. Yet why space-time has this particular structure, why c equals this specific number, remains unexplained, a fundamental parameter we must measure rather than derive. Level 68. Planck's constant. Quantum mechanics is built on a single number, Planck's constant, approximately 6.626 times 10 to the power of minus 34 joule-seconds, representing the minimum unit of action in the universe, the granularity of energy and momentum, the scale at which quantum effects become important. You cannot have less action than 1 unit of Planck's constant. It sets the size of atoms, the wavelength of matter, the uncertainty in position and momentum, the discrete energy levels in quantum systems. If Planck's constant were larger, quantum effects would operate at macroscopic scales. Objects would exhibit wave-like behavior, and classical physics would never emerge. If it were smaller, quantum effects would be confined to tinier scales. Atoms would be smaller, chemistry would operate differently, and the universe would be more classical. The actual value sits precisely where it creates a universe with distinct quantum and classical regimes. Small enough that macroscopic objects behave classically, large enough that atoms have structure and chemistry as possible. But why does it have this value? Planck's constant emerges from quantum mechanics itself. Yet quantum mechanics cannot explain why this particular value, making it an irreducible input parameter that determines the fundamental texture of reality. Level 69. The electron-proton mass. Ratio: the proton weighs 1,836.15 times more than the electron. Not approximately 1,800. Not 2,000, but 1,836.15267 to 9 decimal places. A ratio measured with extraordinary precision, yet unexplained by any fundamental theory. This ratio determines atomic structure. If it were much smaller, atoms would be larger and less stable. If it were much larger, atoms would be more compact and chemical bonds would form differently. The ratio also determines stellar fusion rates, because the weak force interaction that converts protons to neutrons depends on the mass difference between up and down quarks, which connects to the electron-proton ratio through electroweak unification. Change this ratio by 10%, and stellar lifetimes change dramatically. Fusion proceeds at different rates. The universe's thermal history diverges. Yet, despite its importance, despite being measured to 9 decimal places, we have no theory that predicts why the ratio equals 1,836.15 rather than 1,500 or 2,500. The Standard Model treats quark masses and electron mass as independent parameters, leaving this precise ratio as brute fact about nature that determines chemistry and fusion without deeper justification. Level 70. The 3 generations problem. Particles come in 3 families, 3 generations of quarks and leptons, each heavier than the last but otherwise identical in their properties and interactions. The first generation contains the electron, electron-neutrino, up quark and down quark, the building blocks of ordinary matter. The second generation contains the muon, muon-neutrino, charm quark, and strange quark, heavier copies that decay rapidly into first-generation particles. The third generation contains the tau, tau-neutrino, top quark, and bottom quark, even heavier copies that decay even faster. Why 3 generations? Why not 2, or 4, or 17? The Standard Model accommodates 3 families perfectly, but provides no explanation for why nature chose this number. Theorists have explored whether the number 3 emerges from string theory, grand unification, or geometric properties of extra dimensions. But no compelling explanation has emerged. Precision measurements show that only 3 generations of light neutrinos exist. If there were more, they would affect Big Bang nucleosynthesis in ways we don't observe. So, nature contains exactly 3 particle families, a pattern so fundamental that it defines the structure of matter yet so arbitrary that we cannot explain why. Level 71. CP violation. Magnitude. The universe contains matter but almost no antimatter, a asymmetry that requires some difference in how physics treats particles versus antiparticles, a phenomenon called CP violation. Discovered in 1964, when kaon particles decayed in ways that violated the assumed symmetry. The standard model predicts CP violation through a single complex phase in the quark mixing matrix, and measurements confirm it exists with precisely the magnitude the theory predicts, about 1 part in 1,000 for kaon decays. The problem is that this measured CP violation is far too small to explain why the universe contains matter instead of annihilating into pure radiation. To generate the observed baryon to photon ratio of roughly 1 in a billion, you need CP violation about 10 billion times stronger than what we observe. Either unknown sources of CP violation operated in the early universe, new particles, new interactions, new symmetry-breaking mechanisms, or the matter-antimatter asymmetry was built into the initial conditions. The CP violation we've measured is real, precisely quantified, and completely insufficient to explain why you exist, pointing to missing physics in the first microsecond after the Big Bang. Level 72. The QCD phase transition temperature. Quantum chromodynamics, the theory of quarks and gluons, predicts that at sufficiently high temperatures, around 2 trillion degrees Celsius, nuclear matter undergoes a phase transition, transforming from ordinary protons and neutrons into a soup of free quarks and gluons called quark-gluon plasma. This transition happened throughout the universe approximately 1 microsecond after the Big Bang, when the cosmos cooled enough for quarks to condense into hadrons, creating the protons and neutrons that would eventually form atomic nuclei. The transition temperature is approximately 150 mega-electron volts, or 1.7 trillion Kelvin, a specific threshold where the strong force's behavior fundamentally changes. What's remarkable is that this temperature sits precisely where it allows the early universe to create stable hadrons without immediately collapsing into quark matter. If the QCD phase transition occurred at a higher temperature, the universe would have remained quark-gluon plasma longer, potentially preventing nucleosynthesis. If it occurred at a lower temperature, hadronic matter might be unstable. The value emerges from QCD's fundamental parameters, the strong coupling constant and quark masses. Yet these parameters themselves are unexplained inputs that happen to produce a phase transition at exactly the right temperature. Level 73. The Higgs mass. The Higgs boson weighs 125 gigaelectron volts, not 50 gigaelectron volts, not 300 gigaelectron volts, but specifically 125 gigaelectron volts, a value measured with extraordinary precision at the Large Hadron Collider, but utterly unpredicted by theory. The Higgs mass is a free parameter in the Standard Model, something that must be measured experimentally rather than calculated, yet it's arguably the most important mass in physics because it sets the scale of electroweak symmetry breaking and determines the masses of W and Z bosons. What troubles physicists is not just that we cannot predict this value, but that quantum corrections should drive the Higgs mass toward either 0 or the Planck scale, 10 to the power of 16 times heavier, unless contributions from virtual particles cancel with absurd precision. This is the hierarchy problem in its starkest form. The Higgs mass sits at 125 gigaelectron volts, despite receiving enormous quantum corrections that should make it vastly heavier, suggesting either fine-tuning to 35 decimal places or new physics preventing the runaway corrections. Yet searches for this new physics have found nothing, leaving us with a measured Higgs mass that works perfectly, but exists at a value that seems to require unexplained cancellation. Level 74. Neutrino oscillation. Mixing angles. Neutrinos oscillate between 3 types: electron, muon, and tau. As they travel through space, a quantum mechanical effect described by 3 mixing angles that determine the probabilities of flavor transformation. Measurements show these angles have specific values. Theta 12 is approximately 34 degrees. Theta 23 is approximately 45 degrees. And theta 13 is approximately 8.5 degrees. Numbers measured to percent level precision but predicted by no theory. The pattern seems suggestive. Theta 23 is close to maximal mixing. 45 degrees, where muon and tau neutrinos mix equally, while theta 13 is small but non-zero, creating a hierarchy that hints at underlying structure. Some theorists propose that these angles reflect geometric relationships in extra dimensions, or arise from discrete symmetries in neutrino mass generation, or emerge from grand unified theories that relate quark and lepton sectors. Yet, despite decades of work, no theoretical framework successfully predicts all 3 mixing angles from first principles. We measure them with increasing precision, confirming their fundamental parameters that govern neutrino physics, determine oscillation probabilities, affect supernova dynamics and cosmology. Yet we have no idea why they equal 34, 45, and 8.5 degrees, rather than any other combination. Level 75. The Sommerfeld Fine Structure. When you examine the spectrum of hydrogen, the wavelengths of light emitted or absorbed by the simplest atom, you find that each spectral line splits into multiple closely spaced lines, a phenomenon called fine structure that arises from relativistic effects and spin-orbit coupling. The spacing between these lines follows a precise mathematical pattern involving the fine structure constant alpha, with energy splittings proportional to alpha squared, creating a hierarchy where transitions are separated by factors of 1 over 137. This splitting reveals itself in spectra throughout the universe. Distant quasars, stellar atmospheres, nebulae, all showing the same fine structure pattern because alpha has the same value everywhere we look. If alpha were different in distant regions or at early times, we'd see different fine structure spacing in light from distant galaxies. Yet measurements show alpha varies by less than 1 part in 10 to the 5th power, making it one of the most constant numbers in nature. The fact that this dimensionless constant remains precisely 1 over 137.036 across billions of light years and billions of years suggests either it's truly fundamental, woven into space-time itself, or there's a mechanism enforcing its constancy that we haven't identified. The Sommerfeld fine structure stands as cosmic verification that alpha is universally true. Rest break. Pause here for a moment. Let these patterns settle. Notice what you're already seeing differently. How many things you thought were solid turn out to be questions? How many answers dissolve into deeper mysteries? How many constants balance on edges so narrow that the slightest change would unmake everything? What comes next goes to the foundation itself. The final 25 ask, not what we don't know, but what we might never know. Stay with me. Level 76. The measurement problem. Quantum mechanics describes particles as existing in superposition, simultaneously in multiple states, until you measure them, at which point the wave function collapses into a single definite state, producing one specific outcome from the range of possibilities. This wave function collapse is not described by Schrödinger's equation, which governs quantum evolution and is perfectly deterministic and reversible, creating a fundamental divide between unmeasured quantum systems that evolve smoothly and measured systems that jump discontinuously. Nobody knows what causes collapse. The Copenhagen interpretation simply asserts that measurement produces definite outcomes without explaining the mechanism. Many worlds' interpretation denies collapse happens at all, proposing that all outcomes occur in branching parallel universes. Objective collapse theories modify quantum mechanics to make wave functions spontaneously collapse without measurement. But we have no experimental evidence distinguishing these interpretations. No theory of what measurement actually is, no definition of when superposition ends and definiteness begins. The measurement problem has persisted for a century, despite quantum mechanics being our most precisely tested theory, suggesting we're either missing something fundamental or asking a question the theory cannot answer. Level 77. The hard problem of consciousness. You can explain in complete neurological detail how the brain processes visual information. Photons hit retinal cells. Signal cascades trigger neural firing. Patterns propagate through visual cortex. Information integrates across regions. Yet this third-person description never explains the first-person experience of seeing red, the subjective quality of what it's like to perceive color. This is the hard problem of consciousness, explaining why physical processes in the brain produce subjective experience at all, why there's something it's like to be you, why consciousness exists instead of information processing happening in the dark. You can map every neuron, trace every signal, correlate brain states with reported experiences, yet none of this explains why any of it feels like anything. Some philosophers argue consciousness is an illusion, a trick the brain plays on itself, but this relocates the problem. Why would evolution create the illusion if unconscious processing works fine? Others propose consciousness is fundamental, a property of matter like mass or charge, but this makes testable predictions we haven't confirmed. The harder problem persists because materialist neuroscience describes objective processes, while consciousness is inherently subjective, creating an explanatory gap that might be unbridgeable. Level 78. The arrow of time. Fundamental physics is time-symmetric. Newton's laws, Maxwell's equations, Schrödinger's equation. General relativity work equally well running forward or backward in time, describing processes that could reverse themselves without violating any law. Yet the universe exhibits a clear direction. Eggs break, but don't spontaneously reassemble. Heat flows from hot to cold, but never the reverse. Entropy increases but never decreases, creating an arrow of time that points from past to future, despite no fundamental law requiring it. The second law of thermodynamics says entropy always increases, but this isn't a fundamental law. It's a statistical tendency arising because high entropy states are vastly more probable than low entropy states. The real question is why the universe began in such an improbably low entropy state, a condition so far from equilibrium that 13.8 billion years later, we're still experiencing its consequences. If the Big Bang started with maximum entropy, the universe would be a uniform soup with no structure. The fact that entropy was incredibly low at the beginning requires explanation, yet we have none that doesn't invoke special initial conditions or multiverse selection, leaving time's arrow unexplained. Level 79. The black hole information. Paradox. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe forever. No light, no information, no causal connection can escape back out, making black holes perfect information destroyers. But this violates quantum mechanics, which insists information cannot be destroyed, only transformed. a principle called unitarity that's fundamental to quantum theory. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon, slowly evaporating over cosmological timescales. But this Hawking radiation appears to be completely thermal, carrying no information about what fell in. If the black hole evaporates completely, the information vanishes, violating quantum mechanics. Proposed solutions involve radical departures from established physics. Maybe information escapes through subtle correlations in Hawking radiation. Maybe it's preserved in quantum entanglement across the horizon. Maybe black holes store it holographically on their surface. Maybe Hawking radiation isn't actually thermal. Each solution requires modifying either quantum mechanics or general relativity in ways we haven't verified. And 40 years after Hawking identified the paradox, we still don't know how, or whether, information escapes from black holes. Level 80. The nature of dark matter. 85% of the matter in the universe is invisible, detectable only through gravitational effects on visible matter, galaxy rotation curves, gravitational lensing, and structure formation. Yet, despite decades of searching with increasingly sophisticated detectors, we've never directly detected a single dark matter particle. We know dark matter exists because its gravitational influence is unmistakable. Galaxies rotate too fast to hold together without additional mass. Galaxy clusters contain far more mass than visible matter accounts for. The cosmic microwave background's structure requires dark matter. Gravitational lensing shows invisible mass distributions. Every observation confirms dark matter is real and abundant. Yet, every attempt to detect it directly has failed. The leading candidate, weakly interacting massive particles, should occasionally collide with ordinary matter in underground detectors, but no confirmed detection has emerged. Alternative candidates like axions, sterile neutrinos, or primordial black holes each have problems. The disturbing possibility is that dark matter doesn't consist of particles at all, but represents a breakdown in how gravity operates on large scales, or that it's so weakly interacting that direct detection might be fundamentally impossible, leaving us forever inferring its existence from gravitational effects without ever touching it directly. Level 81. The nature of dark energy. 68% of the universe consists of dark energy, an unknown force causing space itself to expand at an accelerating rate, pushing galaxies apart faster despite gravity's attractive pull. Yet we have no idea what it is. Dark energy was discovered in 1998 when astronomers measured distant supernovae and found the universe's expansion is speeding up rather than slowing down, violating every expectation from gravity and matter alone. The simplest explanation is Einstein's cosmological constant, representing the intrinsic energy of empty space. But this raises the vacuum catastrophe. Why is dark energy's density 10 to the power of 120 times smaller than quantum field theory predicts? Alternative explanations invoke quintessence, a dynamic field-filling space whose energy density changes over time, or modifications to general relativity on cosmic scales. Yet, despite 2 decades of observations refining dark energy's properties, we have learned almost nothing about its fundamental nature beyond that it exists, comprises most of the universe's energy budget, and determines cosmic fate. Dark energy could be constant forever, could decay, could strengthen, could reverse and cause cosmic collapse, and we have no theoretical framework predicting which future awaits. Level 82. The initial conditions. Problem. The Big Bang is not a theory of cosmic origin, but a description of cosmic evolution from an initial hot, dense state. It tells you how the universe developed, but says nothing about why it started with those specific conditions. Why did the universe begin with incredibly low entropy, nearly perfect homogeneity, precise flatness, and exactly the right energy density? These aren't predictions from theory, but initial conditions inserted by hand, fine-tuned parameters that determine everything that follows. Inflation theory attempts to solve some problems by proposing exponential expansion that would flatten space and smooth out inhomogeneities. But inflation itself requires special initial conditions. Why did the inflaton field exist? Why did it have the right potential energy? Why did inflation begin and end when it did? You're left either accepting that the universe started with extraordinarily unlikely conditions for no reason, or invoking a multiverse where different regions have different initial conditions, and we exist in one that permits structure, or admitting that the question why these initial conditions might be unanswerable within physics because any theory of origins must start somewhere. Level 83. The vacuum metastability. The Higgs field that permeates all of space might not be sitting in its lowest possible energy state. Calculations using the measured Higgs mass and top quark mass suggest the vacuum could be metastable, meaning it's stable for now, but could potentially decay to a lower energy state if given sufficient energy. If vacuum decay occurs anywhere in the universe, it would propagate outward at light speed, as an expanding bubble of true vacuum with different physical constants, different particle masses, different laws of physics, destroying everything in its path, and restructuring reality according to new rules. The possibility is real. Quantum field theory permits metastable vacua, and the measured Higgs mass sits right at the boundary between stability and metastability. Yet the universe has persisted for 13.8 billion years without vacuum decay, suggesting either we're in a truly stable vacuum despite calculations suggesting otherwise, or the metastable lifetime is far longer than the current age of the universe, or we're extraordinarily lucky. This uncertainty means we don't even know if the reality we inhabit is fundamentally stable or just temporarily stable, existing in a false vacuum that could collapse at any moment. Level 84. The singularity problem. According to general relativity, if you reverse cosmic expansion and run time backward, you eventually reach a moment when all matter and energy occupies zero volume, creating infinite density, infinite temperature, infinite curvature. A singularity where mathematics breaks down and physics stops making predictions. This is T equals 0, the Big Bang singularity, where general relativity fails because it describes space-time using smooth geometry that cannot handle infinite curvature. The same problem appears at black hole centers. General relativity predicts matter continues collapsing until it forms a point of infinite density. But infinities in physics usually signal that your theory is incomplete. When you get infinite answers, it means you're applying the theory outside its valid domain. Quantum mechanics should become important at extremely small scales, preventing true infinities. Yet we have no consistent theory of quantum gravity to describe what actually happens at ET equals 0 or inside black holes. The singularity problem suggests either our understanding of spacetime is fundamentally wrong, or singularities are shielded from observation, or the question, what happened at TTAs equals 0, is malformed because time itself emerges from quantum gravity. Level 85. The emergence of spacetime. Most approaches to quantum gravity suggest that space-time is not fundamental but emergent. That smooth, four-dimensional spacetime arises from some deeper quantum structure, the way temperature emerges from molecular motion. String theory proposes spacetime emerges from vibrating strings in higher dimensions. Bloop quantum gravity builds space from discrete networks of quantum geometry. ADS/CFT suggests spacetime can emerge holographically from quantum field theory on a boundary. But all these frameworks struggle with the same question. If spacetime emerges, what does it emerge from, and how? The problem is circular. We describe quantum mechanics using time evolution and spatial configurations. Yet, if spacetime emerges from quantum mechanics, the theory cannot assume time and space exist beforehand. Some physicists propose that quantum entanglement is the fundamental ingredient from which spacetime geometry emerges, with connectivity reflecting patterns of entanglement. But this raises new questions about what exists before entanglement creates geometry. The emergence of spacetime is not just a technical problem in quantum gravity, but a conceptual crisis. If the stage on which physics operates is itself emergent, what does fundamental even mean? Level 86. Quantum gravity. General relativity and quantum mechanics are both extraordinarily successful theories. General relativity describes gravity, space-time, and cosmology with exquisite precision. Quantum mechanics governs atoms, particles, and forces with unmatched accuracy. Yet they are fundamentally incompatible, making different, irreconcilable predictions about what happens when gravity becomes quantum. At the Planck scale, roughly 10 to the power of minus 35 meters and 10 to the power of minus 43 seconds. Both quantum effects and gravitational effects become equally important, creating a regime where you need quantum gravity to make predictions, but we have no complete theory that works. String theory, loop quantum gravity, causal set theory, asymptotic safety. Every approach to quantum gravity involves speculative mathematics, requires dimensions or structures we've never observed, makes few testable predictions, and remains incomplete after decades of work. The fundamental obstacle is that general relativity treats spacetime as a smooth geometric manifold, while quantum mechanics treats everything as discrete quantum fields, creating a conceptual mismatch that resists resolution. We don't just lack the right equations. We might lack the right conceptual framework for thinking about quantum gravity, making this less a missing theory and more a fundamental limit on how we understand nature when geometry itself becomes quantum. Level 87. The firewall paradox. The black hole information paradox took a disturbing turn in 2012, when physicists realized that preserving quantum mechanics might require black holes to have firewalls. Walls of extremely high-energy particles just inside the event horizon that would incinerate anything falling through, violating the equivalence principle, which says that falling into a black hole should feel like floating in free space. The argument is technical, but the implications are stark. If Hawking radiation carries away information, it must be entangled with radiation emitted earlier. But that same radiation is also supposed to be entangled with the black hole interior, creating a three-way entanglement that quantum mechanics forbids. Something has to give. Either the equivalence principle is wrong and firewalls exist, or quantum mechanics is wrong and entanglement can be cloned, or locality is wrong and information can escape through non-local connections, or black hole interiors don't exist the way general relativity describes. Each option requires abandoning a foundational principle of physics, and years of intense debate haven't produced consensus on which principle should be sacrificed. The firewall paradox reveals that our most fundamental theories cannot all be right simultaneously when black holes are involved. Level 88. The ER equals EPR conjecture. Einstein-Rosen bridges are wormholes, shortcuts through space-time connecting distant regions, predicted by general relativity, but never observed, and generally considered more mathematical curiosity than physical reality. Einstein-Podolsky-Rosen pairs are entangled particles, quantum systems that remain mysteriously correlated across arbitrary distances, creating spooky action at a distance that Einstein found troubling, but experiments confirm exists. The ER equals EPR conjecture proposes that these seemingly unrelated phenomena are actually the same thing. That quantum entanglement between particles is literally a geometric wormhole connection through space-time, making every entangled pair connected by a microscopic Einstein-Rosen bridge. If true, this would unify quantum mechanics and general relativity in unexpected ways, explaining entanglement as geometric connection and potentially resolving the black hole information paradox by allowing information to escape through quantum connections. But the conjecture raises as many questions as it answers. How can microscopic wormholes exist without being detectable? Why would quantum correlations require geometric tunnels? And what does this imply about space-time structure when every entangled particle is connected by wormhole threads? The ER equals EPR conjecture sits at the intersection of quantum information and quantum gravity, suggesting deep connections we don't yet understand. Level 89. The cosmological principle. The cosmological principle states that the universe is homogeneous and isotropic. It looks the same in all directions and from all locations on large scales, a foundational assumption underlying all of modern cosmology, built into Friedman equations, cosmic expansion models, Big Bang theory, everything. Observations broadly support this. The cosmic microwave background is uniform to 1 part in 100,000. Galaxy distributions appear homogeneous when averaged over hundreds of millions of light years, but recent observations hint at violations. Galaxy peculiar velocities suggest bulk flows larger than the cosmological principle allows. The CMB dipole is anomalously aligned. Some quasar distributions show patterns inconsistent with statistical isotropy. The Hubble tension might indicate different expansion rates in different directions. If the cosmological principle is wrong, if the universe has preferred directions, large-scale inhomogeneities, or observational properties that depend on location, then decades of cosmological analysis rests on invalid assumptions. Dark energy measurements might be artifacts of inhomogeneity, and our position might not be typical. The principle seemed philosophically motivated, Copernican modesty suggesting we're not special. But if observations demand we abandon it, cosmology faces a crisis because almost every model assumes homogeneity and isotropy from the start. Level 90. The multiverse problem. Eternal inflation, string theory, quantum mechanics, many worlds interpretation, and various theoretical frameworks suggest our observable universe is just one among countless others. A multiverse where different regions have different physical constants, different laws, different dimensionalities. This multiverse hypothesis solves some problems. It explains fine-tuning by saying all possible universes exist, and we're in one compatible with observers. It makes inflation's initial conditions generic. It provides natural explanations for arbitrary parameters. But it creates a deeper crisis. If anything that can happen does happen somewhere in the multiverse, the theory makes no testable predictions, because every observation is consistent with some universe existing where that observation occurs. You cannot falsify a multiverse theory that predicts all possible outcomes. This threatens the scientific method itself. Physics has always worked by making predictions that could be proven wrong, but multiverse theories evade falsification by construction. Some physicists argue we can still make probabilistic predictions using anthropic reasoning. Others argue untestable theories aren't science regardless of elegance, and the debate has persisted without resolution. The multiverse problem asks whether physics can explain reality using theories that predict everything, and therefore predict nothing. Level 91. The origin of physical laws. Physics describes the universe using laws, equations that govern how particles move, how forces interact, how energy transforms. But it cannot explain why these particular laws exist rather than different ones. Why does gravity follow an inverse square law? Why do electric charges attract and repel according to Coulomb's equation? Why does entropy increase? These laws could have been different. You can write down alternative universes with different force strengths, different symmetries, different particle properties. Yet our universe follows this specific set of rules with no deeper explanation. Some physicists argue that a theory of everything might derive all physical laws from a single principle, reducing the arbitrariness. But this just relocates the mystery. Why that principle? String theory suggests that different solutions correspond to different possible universes with different laws, making our laws a consequence of which solution nature selected. But this doesn't explain why string theory's equations are the fundamental rules. The origin of physical laws sits at the boundary of physics and metaphysics, asking questions that might be scientifically unanswerable because any answer must invoke laws or principles that themselves remain unexplained. Level 92. The problem of time in quantum gravity. In general relativity, time is part of space-time, a dimension woven together with space, flexible and dynamic, bending in response to mass and energy. In quantum mechanics, time is absolute, a fixed parameter that evolves wave functions forward, never varying, always marching in one direction. These incompatible treatments create profound problems when trying to unify relativity and quantum mechanics. The Wheeler-DeWitt equation, the closest thing we have to a quantum theory of the universe, contains no time variable at all, describing a static quantum state with no evolution, suggesting that time might not exist at the most fundamental level. If true, this means the flow of time you experience, past, present, future, causality, change, emerges from something timeless. But what does it mean for physics to operate without time when every quantum equation uses time evolution? Every observation occurs at a moment. The problem of time in quantum gravity isn't just technical mathematics. It's a conceptual crisis about whether one of the most basic aspects of experience is real or illusory, fundamental or emergent. Level 93. The holographic principle. The holographic principle proposes that all information in a three-dimensional region of space can be encoded on its two-dimensional boundary, suggesting that reality, with depth, volume, and three spatial dimensions, might be a projection from information stored on a distant surface. This emerges from studying black holes. The information content of a black hole is proportional to its surface area, not its volume, implying three-dimensional space might not be fundamental. The ADS/CFT correspondence in string theory provides a concrete example where a quantum field theory on a boundary is mathematically equivalent to a gravitational theory in the bulk, demonstrating that holographic encoding actually works. If the holographic principle is true for our universe, space-time dimensions are not what they appear. You might be a two-dimensional pattern of information that experiences itself as three-dimensional. The universe, a cosmic hologram projected from some distant boundary. This raises disturbing questions. What is the boundary? Where is it? What encodes the information? And why does the projection create the illusion of depth? The holographic principle blurs physics and ontology, suggesting that dimensional structure itself might be emergent rather than fundamental. Level 94. The simulation. Hypothesis. The simulation hypothesis proposes that we might be living inside a computer simulation run by an advanced civilization, a suggestion that connects to physics through probability arguments. If technological civilizations eventually develop the ability to run detailed simulations of universes, creating virtual worlds populated by conscious entities, then the number of simulated universes will vastly outnumber base reality, making it statistically likely that any given conscious observer exists in a simulation. Some physicists point to suggestive features. The universe appears to follow computable laws. Quantum mechanics introduces discrete units that resemble pixels. The Planck scale sets a minimum resolution below which physics breaks down. But the hypothesis is unfalsifiable. Any observation is consistent with simulation because the simulators could have programmed anything, making it scientifically useless even if philosophically intriguing. You can't test whether you're in a simulation because any test result could be simulated, creating an epistemic trap where the question is meaningful but unanswerable. The simulation hypothesis reveals the limits of scientific inquiry. Some questions about the nature of reality might be structurally beyond what observation and experiment can resolve. Level 95. The ultimate fate of the universe. The universe's ultimate fate depends on dark energy's behavior, and because we don't understand dark energy, we can't predict with certainty what happens in the far future. If dark energy remains constant, the cosmological constant scenario, the universe will continue expanding forever. Galaxies will recede beyond each other's cosmic horizons. Star formation will cease. Black holes will slowly evaporate through Hawking radiation, and in 10 to the power of 100 years, the universe will reach maximum entropy, a cold, dark, empty state called heat death, where no gradients exist, no energy flows, nothing changes. If dark energy strengthens over time, the Big Rip scenario, acceleration will increase until it tears apart galaxies, then solar systems, then planets, then atoms, eventually ripping space-time itself. If dark energy decays or reverses, currently less favored, expansion could halt and reverse, causing the universe to collapse back into a hot, dense state in a big crunch. Each fate is determined by a single parameter: dark energy's equation of state, a number we've measured to 10% precision but don't understand theoretically. Humanity's existence occupies the first 0.00000000001% of cosmic history, a brief moment in a universe whose ultimate destination remains unknown. Level 96. The before the Big Bang problem. General relativity describes the Big Bang as the beginning of space-time itself, not an explosion in pre-existing space, but the origin of space and time together, making what happened before the Big Bang potentially meaningless because before assumes that time existed beforehand. But this answer feels unsatisfying. Some theories propose that the Big Bang wasn't the beginning, but a transition. Eternal inflation suggests our universe budded off from a larger inflating space-time. Loop quantum gravity proposes a previous contracting universe bounced into expansion. String theory allows for cyclic cosmologies where universes endlessly expand and contract. Yet all these theories either invoke eternal structures that never began, shifting the problem, or eventually hit a boundary where physics breaks down. The deepest issue is that physics operates within time, using causality and evolution. So any theory of cosmic origin must either explain where time came from or accept time as fundamental and unexplained. Asking what happened before the Big Bang might be a category error, like asking what's north of the North Pole, or it might be a genuine question that physics cannot answer because the tools of physics cannot operate outside space-time. Level 97. The Anthropic Principle. The anthropic principle observes that the universe must have properties compatible with the existence of observers, because if it didn't, there would be no observers to notice. This sounds tautological, but becomes powerful when combined with fine-tuning. If the universe can have many configurations, and most don't allow observers, then the fact that we exist tells us something about which configuration we're in. The weak anthropic principle simply notes this selection effect. The strong version suggests the universe must have properties that allow observers to arise, implying some teleological necessity. But anthropic reasoning creates uncomfortable questions. Does it count as explanation to say, the universe has these properties, because if it didn't, we wouldn't be here? Or is this circular reasoning? Does anthropic selection require a multiverse? If we use anthropic reasoning, what predictions can we make? And how do we avoid explaining everything as necessary for observers without deeper understanding? The anthropic principle sits at the intersection of physics, philosophy, and probability theory, accepted by some physicists as legitimate reasoning and rejected by others as untestable speculation. Level 98. The problem of induction. Science proceeds by induction, observing patterns, formulating hypotheses, testing predictions, building confidence that laws will continue holding in the future. But philosopher David Hume identified a fundamental problem. There's no logical justification for assuming the future will resemble the past. The fact that gravity worked yesterday provides no guarantee it will work tomorrow unless you assume nature is uniform across time. But that assumption cannot be proven without circular reasoning. You might say, induction has worked before, therefore it will work again. But this uses induction to justify induction. Karl Popper tried to solve this through falsification. Science doesn't prove theories true, but tentatively accepts theories that survive attempts to prove them wrong. But falsification still relies on induction, because you assume that a theory falsified today will remain falsified tomorrow. The problem of induction reveals that science's empirical foundation rests on an unprovable assumption, that the universe follows consistent laws across time and space. This assumption works extraordinarily well in practice, allowing us to build technology and predict phenomena, but it cannot be derived from logic or observation alone, making it an article of faith embedded in the scientific method. Level 99. The Gödel incompleteness of physics. Kurt Gödel proved that any sufficiently complex formal system contains statements that are true but unprovable within the system. No matter how many axioms you add, there will always be true statements that cannot be derived. This theorem applies to mathematics, but does it apply to physics? If physical laws can be encoded as mathematical statements, and if the universe follows consistent rules, then Gödel's incompleteness suggests there might be true facts about nature that are unprovable from any finite set of physical principles. Some physicists argue that this sets a fundamental limit on science. Not every question has an answer derivable from observation and theory. Others argue that physics is fundamentally different from mathematics because it's constrained by empirical observation. Nature decides truth, not logical consistency, making Gödelian limitations irrelevant. The question connects to deeper issues. Is mathematics discovered or invented? Are physical laws mathematical objects or descriptions of nature? Can physics be complete, deriving all phenomena from first principles? Or does Gödel guarantee that some truths will remain forever beyond theoretical explanation? The Gödel incompleteness of physics asks whether logic itself places absolute limits on what science can achieve. Level 100. The unknowability limit. There are truths about the universe that might be forever beyond human comprehension. Not because we lack the right instruments or mathematics, but because of fundamental limits built into the structure of knowledge itself. Observable universe boundaries restrict what we can see. Regions beyond our cosmic horizon are causally disconnected, forever inaccessible. Quantum mechanics might place limits on what can be measured simultaneously. Gödel's theorems might prevent certain truths from being derived from any axioms. Consciousness might involve subjective properties that third-person science cannot capture. Some questions, why do these laws, why does anything exist, might be malformed, unanswerable, or require frameworks we cannot conceive. The history of science shows relentless progress, mysteries becoming explanations. Yet it also reveals deeper mysteries beneath each solution. An endless regression where every answer generates new questions. The unknowability limit acknowledges that reality might contain layers forever beyond reach, truths that exist but cannot be known, mysteries that will never resolve because the tools required, observation, reason, mathematics, consciousness itself, are fundamentally limited. Perhaps the deepest truth is that some truths remain permanently hidden, and learning to accept that uncertainty is the final lesson that keeps scientists awake at night, wondering what lies just beyond the edge of the knowable. Closing thoughts. 100 mysteries. You started with familiar questions. Why we sleep, why we yawn, why zebras have stripes, and ended at the edge of the knowable, staring into questions that might not have answers. Some of you made it all the way through. Some drifted off somewhere in the middle, which is exactly what this was designed for. Either way, you've spent time with the unanswered, the unexplained, the permanently mysterious. The universe keeps more secrets than it reveals. Every answer we find opens 10 new questions. Every solved mystery points toward something deeper we don't understand. That's not a failure of science. It's the nature of curiosity. The edge of knowledge keeps moving, but it never disappears. If you want more like this, more mysteries, more late-night wondering, more questions that don't resolve, subscribe. There's always another layer to explore, another 100 things we thought we understood that turn out to be far stranger than we imagined. Sleep well. Let the questions linger. Some of them might still be here in the morning.